Hello there, and welcome to Nightfall Science. Tonight, we drift gently into a quiet possibility that humanity may not be late to the universe, but early in the long story of life among the stars. Let your shoulders ease away from the day, and let your eyes grow heavy whenever they wish. The universe has been unfolding for billions of years, and it may keep making new worlds long after we fall asleep. Let's begin. Humanity may be early in the universe's living story. When people ask why the universe seems so quiet, they often imagine that life should already be everywhere. The stars are old, the galaxy is wide, planets are common. It feels natural to think that if other civilizations exist, many of them should have appeared long before Earth. But there is another possibility, softer and less familiar. Perhaps humanity is not late. Perhaps humanity is early. Perhaps the universe is still young in the ways that matter for life: planets, chemistry, and intelligence. The universe is about 13.8 billion years old. That sounds ancient, and it is ancient compared with a human life. But many stars can last far longer than the sun. Red dwarf stars, the smallest and most common stars, may shine for hundreds of billions or even trillions of years. Their long lives mean the future may contain far more time for planets than the past has contained so far. This changes the feeling of cosmic silence. The quiet sky may not mean that no one exists anywhere. It may mean that many possible living worlds have not had time to unfold. The universe may still be preparing many of its future homes. Earth may be one of the early places where matter became aware enough to ask questions. A quiet universe may not be finished. It may still be at the beginning of its long biological dawn. The universe began without planets. In the earliest times after the Big Bang, there were no worlds, no moons, no oceans, and no rocks. The young universe was hot, dense, and filled with simple particles. Later, as it cooled, the first atoms formed, mostly hydrogen and helium. These were the simplest ingredients. Planets like Earth need heavier elements. They need carbon, oxygen, silicon, iron, magnesium, sulfur, and many others. These elements did not exist in large amounts at the beginning. They had to be made inside stars. The first stars were not born into a universe ready for life. They were born into a universe still learning how to make complexity. Inside their cores, nuclear fusion built heavier elements from lighter ones. When massive stars ended their lives, they released those elements into space. New stars formed from enriched gas. Around some of those stars, rocky planets became possible. This means the universe needed time before it could build habitable worlds. It needed generations of stars. It needed explosions, winds, clouds, dust, and the slow gathering of material. Life could not appear immediately, because the necessary chemistry was not yet widely available. The early universe was not empty of beauty. It had light, gravity, stars, and structure, but it did not yet have the full toolkit for oceans, continents, and cells. Before life could begin, the universe had to make the ingredients of stone and breath. The first stars prepared the way for later worlds. The first stars are often called population 3 stars. They are thought to have formed from nearly pure hydrogen and helium, with very few heavier elements. Because of this, many may have been massive, bright and short-lived compared with stars like the Sun. These first stars did not host Earth-like planets in the way later stars could. Their environment lacked enough heavy elements to build rocky worlds easily, but their role was still essential. They acted like cosmic furnaces. They created heavier elements and spread them outward when they died. After the first stars, the universe became more chemically rich. Gas clouds contained more carbon, oxygen, silicon, iron, and other elements. Later generations of stars formed from this enriched material. Around them, dust grains could gather into pebbles, planetesimals, and eventually planets. This is one of the quiet rhythms of cosmic history. The first stars did not need to host life in order to help life. They prepared the universe for everything that came later. Their brief lives became part of the long patience of biology. Earth's atoms carry this deep history. The iron in the planet, the oxygen in the oceans, and the carbon in living cells all come from older stars. Life is not separate from stellar history. It is made possible by it. The first stars were not homes. They were the first lamps that helped the universe become ready for home. Rocky planets needed cosmic enrichment. A rocky planet is not simple to build. It needs solid materials, metals, silicates, minerals, and dust. These materials form from heavier elements. Without them, a star may shine, but it may not have Earth-like planets around it. Over time, galaxies become enriched. Each generation of stars returns processed material to space. Supernovae, stellar winds, and merging stars add new elements to the interstellar medium. Future stars form from gas that carries this growing chemical inheritance. This means rocky planets may have become easier to form as the universe aged. Early in cosmic history, there may have been fewer places where Earth-like chemistry could gather. Later, more stars formed with enough heavy elements to support planetary systems. Astronomers call the abundance of elements heavier than hydrogen and helium metallicity. A star's metallicity can influence the kinds of planets that form around it. Giant planets are more common around stars with higher metallicity. Rocky planets can form across a wider range, but they still need solid building blocks. The important idea is gentle. The universe's ability to build living worlds may have improved with time. The future may contain many more chemically prepared systems than the deep past did. Earth did not appear at the universe's beginning. It appeared after billions of years of stars quietly enriching the dark. The Sun was born from older stars' remains. The Sun is not a first-generation star. It formed about 4.6 billion years ago from a cloud of gas and dust that had already been enriched by earlier stars. That cloud contained the ingredients needed to build planets, asteroids, comets, moons, and eventually life. The solar system formed from a rotating disk around the young Sun. Dust grains collided and stuck together. Pebbles became larger bodies. Planetesimals became planetary embryos. Over time, the rocky inner planets formed, and the giant planets gathered farther out. Earth inherited the chemical work of the galaxy. Its rocks contain elements forged in older stellar interiors and spread by stellar endings. Its oceans contain hydrogen from the early universe and oxygen made in stars. Its living organisms are built from carbon, nitrogen, phosphorus, sulfur, and metals that were once part of interstellar material. This makes Earth feel both young and ancient. The planet itself is about 4.5 billion years old, but its atoms belong to a much older story. They passed through stars, clouds, and dust before becoming soil, water, and cells. If humanity is early, it is not because Earth appeared at the beginning. Earth appeared after long preparation. But compared with the vast future of many stars, Earth may still have arrived near the beginning of the universe's life-friendly era. A young world can be made from very old light. The Sun is middle-aged, but many stars will live far longer. The Sun has shone for about 4.6 billion years. It will continue on the main sequence for several billion more before slowly changing into a red giant. For Earth, the Sun's life sets a limited window. The planet cannot remain habitable forever. But the Sun is not the longest-lived kind of star. Smaller red dwarf stars burn their fuel much more slowly. They are dimmer and cooler, but they can last for immense periods of time. Some may shine for hundreds of billions or even trillions of years. This is astonishing when placed beside the current age of the universe. The universe is not old enough for any red dwarf to have reached the end of its normal life. All red dwarfs ever formed are still young in that sense. Their long futures remain almost entirely ahead. If planets around some red dwarfs can remain habitable, then the universe's future may contain enormous opportunities for life. Many possible living worlds may orbit stars that are still in their early chapters. Their biology, if it appears, may unfold long after the Sun is gone. This does not mean red dwarf planets are easy homes. They can face flares, tidal locking, and atmospheric challenges. But because red dwarfs are so common and long-lived, they matter deeply. The universe may have built many slow lamps whose longest stories have barely begun. Red dwarfs may dominate the future of life. Red dwarfs are the most common stars in the Milky Way. They are small, cool, and faint. Because they use fuel slowly, they can remain stable for times far longer than stars like the Sun. In the very distant future, when larger stars have faded, red dwarfs may continue glowing quietly. This gives them a special place in thinking about future life. If even a fraction of red dwarf planets can support biology, then much of the universe's future life may belong to these small stars. Their planets may have long ages in which chemistry can explore, adapt, and become complex. A planet around a red dwarf must orbit close to receive enough warmth. This closeness can bring challenges. The planet may become tidally locked, with one side always facing the star. It may experience stellar flares, especially when the star is young. Its atmosphere may be shaped by radiation and charged particles. Yet none of these challenges automatically closes the question. Atmospheres and oceans can move heat. Planets may retain air under some conditions. Some red dwarfs become calmer with time. A world that survives the early active period may have an extremely long future. If humanity is early, then red dwarf systems may be one reason. Many of their possible biospheres may not have matured yet. Their clocks run slowly. Around the smallest stars, the future may have more time than the past can imagine. The quiet sky may be young in biological time. The universe's age can be measured in billions of years, but biological time is different. Life needs suitable planets, stable conditions, useful chemistry, energy, and long intervals. A star may be old, yet its planets may not be easy homes. Another star may be young, but its planets may already be alive. Earth took billions of years to produce complex life. Microbes appeared early, but animals came much later. Technological intelligence arrived only in the final moment of Earth's story. If this slow pattern is common, then many living planets may still be in microbial stages. Others may not yet have begun life at all. This means the galaxy's silence may not be a sign of emptiness. It may be a sign of timing. Worlds may need long, calm histories before minds can appear. Many planets may still be waiting for their own chemistry to cross the threshold into biology. The phrase young universe can sound strange because the cosmos is ancient. But compared with the possible lifetimes of red dwarfs, the current universe is still early. Compared with trillions of years of future starlight, 13 billion years is only a beginning. Perhaps the universe is not late in its story of life. Perhaps it is still learning how many living worlds it can become. Earth appeared during a period rich with star formation. The Milky Way has been forming stars for billions of years. The rate of star formation has changed over time, rising and falling as gas clouds collapse, stars are born, and material is recycled. The Sun formed during a time when the galaxy had enough heavy elements to build rocky planets like Earth. This timing matters. If Earth formed too early, the ingredients for rocky planets and complex chemistry may have been less abundant. If it formed much later, it might orbit a different kind of star or exist in a different galactic environment. Earth belongs to a particular window in cosmic history. But a window is not the whole story. Many stars are still forming today. Many will form in the future, though the rate may slowly decline. Existing red dwarfs will continue shining for immense stretches. Planets already formed may remain stable for ages. This means Earth is not necessarily typical of all life-bearing worlds across cosmic time. It may be part of an early wave of complex life around sun-like stars. Later waves, if they happen, may occur around smaller, longer-lived stars. The universe's living story may not be evenly spread. It may have chapters. Earth may belong to one of the first chapters where rocky planets, stable stars, and enough chemical richness came together. A chapter can be early and still feel ancient to those living inside it. The future universe may contain more possible living years than the past. When people think about life in the universe, they often count planets, but another way to think is to count time. A planet that stays habitable for 10 billion years offers more opportunity than one that stays habitable for 1 billion. A red dwarf planet that remains stable for hundreds of billions of years may offer a vast biological future. From this view, the universe's future may contain more habitable planet years than its past. Many small stars will continue shining long after sun-like stars age away. If some of their planets remain suitable, then the total opportunity for life may be weighted toward the future. This idea makes humanity's moment feel unusual. Earth exists around a star that will not last forever. Life here has already had billions of years, yet the universe as a whole may have far more time ahead. The long future may contain worlds that are still young, planets that have not yet cooled into stability, and biospheres that have not yet begun. It is possible that life is rare. It is possible that red dwarf planets are difficult homes. It is possible that many future worlds never become alive. But the time available is enormous. The silence of the stars may not mean life has failed to appear. It may mean much of life's possible time has not arrived yet. The question changes from where is everybody to when is everybody. The Fermi Paradox often asks, where is everybody? It looks across space. It imagines other civilizations spread among the stars and wonders why none have been found. But if humanity may be early, the question changes. It becomes, when is everybody? This version is softer. It does not assume that all civilizations should already exist. It allows for the possibility that many worlds are still preparing. Their stars may still be young. Their planets may still be changing. Their oceans may still be forming. Their chemistry may still be moving slowly toward life. Time becomes a kind of distance. A civilization a billion years in the future is as unreachable as one beyond the horizon of space. It may be real in the universe's total story, but not present now. Earth cannot hear signals from civilizations that have not yet begun. This perspective does not solve the mystery completely. There may still be older stars, older planets, and possible places where life could have appeared long ago. But it adds another layer. The silence may be partly caused by cosmic scheduling. Humanity may not be alone in the final sense. It may simply be awake during an early quiet hour. Some questions are answered only by waiting. Science can study the past through light, rocks, fossils, and cosmic background radiation. It can study the present with telescopes and spacecraft. But the future can only be modeled, imagined, and approached slowly. Whether the universe will produce many future civilizations cannot be observed directly now. It depends on how planets evolve, how long atmospheres last, how often life begins, how red dwarf systems behave, and whether intelligence commonly appears. These are scientific questions, but many answers will take time. Future telescopes may reveal more about planets around red dwarfs. Future missions may study atmospheres and biosignatures. Future generations may learn whether Earth is early, ordinary, or rare. The answer may unfold over centuries. This is peaceful in a sleep science journey. The unknown does not have to be rushed. Some truths arrive through patient accumulation. A spectrum here, a planet there, a sample returned, a moon studied, a signal checked and checked again. The universe has waited billions of years to produce beings who ask about its silence. It can wait longer to answer. Some mysteries are not closed doors. They are slow-opening windows, lit from the far side by time. Part 2 of 9. Most stars are smaller than the Sun. The Sun feels ordinary because it is the star Earth knows best. It rises, warms the surface, drives weather, feeds plants, and lights the day. But in the wider galaxy, the most common stars are not like the Sun. They are smaller, cooler, dimmer red dwarfs. Red dwarfs make up most of the stars in the Milky Way. They are quiet in appearance, but important in number. Because they are so common, many planets in the galaxy may orbit them. Any story about life in the universe must eventually pass through these small stars. Their long lives make them especially interesting. A star like the Sun shines steadily for about 10 billion years before leaving its main sequence stage. A red dwarf can last far longer. Some may continue shining for hundreds of billions or trillions of years. That is far beyond the present age of the universe. This means the current universe has not yet seen the full history of red dwarf planets. None of these stars has had time to grow old in the way the Sun will. Their planets may still be in early chapters. Their longest possibilities remain ahead. If life can develop on some red dwarf worlds, then the future may hold many more opportunities than the past. The galaxy's silence today may partly reflect that many of its longest-lived stars have not yet allowed their deepest stories to unfold. The smallest stars may keep the longest secrets. A red dwarf's habitable zone lies close to the star. Because red dwarfs are dim, their habitable zones are close in. A planet must orbit near the star to receive enough warmth for liquid water on its surface. Such a planet may complete an orbit in days or weeks, not months or years. This close orbit makes red dwarf planets easier to find in some ways. When a planet crosses in front of a small star, it blocks a larger fraction of the star's light. Telescopes can notice the dimming more easily. A close orbit also means transits happen more often, giving more chances to study the planet. But closeness changes the planet's environment. The star may pull strongly on the world, shaping its rotation. Over time, the planet may become tidally locked, keeping one side always facing the star. One hemisphere may live under constant daylight, while the other rests in endless night. At first, this sounds unlike Earth. But climate does not depend only on sunlight. Air and oceans can move heat. Winds can flow from day side to night side. Clouds can form over the bright side and reflect light. The boundary between day and night may hold steady, mild regions. A red dwarf planet does not need to copy Earth to be interesting. It may have its own climate logic, its own rhythms, and perhaps its own forms of stability. A world can live beneath a fixed sun and still have moving weather. Tidally locked planets may have permanent twilight. On a tidally locked planet, the same side always faces the star. Near the center of the day side, the star may hang high and still in the sky. On the far night side, the star never rises. Between them lies a twilight region, where the star may rest near the horizon forever. This region is sometimes imagined as a possible place for milder conditions. If the day side is too warm and the night side too cold, the border between them may offer balance. Winds, oceans, and clouds could help spread heat around the planet. The climate would depend on many details. The thickness of the atmosphere matters. The presence of oceans matters. The amount of starlight matters. The planet's rotation, clouds, surface pressure, and geography all matter. A thin atmosphere might fail to move enough heat. A thicker one might create a more connected world. Life, if it existed there, would not experience days like Earth's. There may be no sunrise, no sunset, no changing noon. Instead, organisms might live under a star that never shifts much in the sky. They might follow chemical cycles, weather cycles, tides, or internal biological rhythms. This kind of world expands imagination. The universe may create habitable settings that feel strange but remain gentle enough for life. Some future biospheres may grow under a sky of endless evening. Young red dwarfs can be restless. Red dwarfs live for a very long time, but their early years can be active. Many young red dwarfs produce strong flares. They release bursts of radiation and charged particles. For planets orbiting close to the star, this activity can shape atmospheres and surfaces. A planet in a red dwarf habitable zone may therefore face a difficult beginning. Its atmosphere may be eroded. Its water may be affected by high-energy light. Its surface may receive strong radiation before the star becomes calmer. This does not automatically end the possibility of life. A planet may begin with a thick atmosphere. It may have a magnetic field. It may keep water underground or beneath ice. It may develop life later, after the star's activity settles. It may be protected by oceans, rock, or dense air. The important point is timing. Red dwarf planets may need to survive their star's active youth before their long, stable future begins. If many can survive, then their later ages may be extraordinarily long and calm. If few can survive, then red dwarfs may be less friendly to life than their numbers suggest. This question remains one of the most important in astrobiology. Red dwarfs offer time, but time alone is not enough. Life also needs an environment that can keep its essential ingredients. A small star may begin with restless light, then settle into a very long glow. Some planets may wait for their stars to calm. A world around a red dwarf may not be ready for life immediately. Its early atmosphere may be changing. Its surface may be too exposed. Its oceans, if present, may be affected by stellar activity. But as the star ages, conditions may grow more stable. This creates the possibility of delayed habitability. A planet may begin in a difficult state, then become gentler later. Water may remain underground, locked in minerals, or preserved beneath ice. Volcanic activity may renew the atmosphere. Impacts or interior processes may bring gases to the surface. Over time, the world may enter a calmer chapter. Earth's own habitability changed over time. Early Earth was not the same as modern Earth. Its atmosphere, oceans, continents, and biosphere evolved together. Life did not require the planet to begin in its present form. It emerged in one era and transformed the next. Red dwarf planets may have even longer timelines. If they can keep water and atmosphere through early challenges, they may have hundreds of billions of years ahead. Their biological stories, if they begin, could unfold slowly. This possibility supports the idea that humanity may be early. Many red dwarf worlds may still be in preparation. Their stars may still be settling. Their climates may still be finding balance. Their chemistry may not yet have crossed into life. The future may contain planets that are not ready yet, but may one day become softly alive. The universe's star formation peaked long before today. The universe does not form stars at the same rate forever. Long ago, star formation was more active. Galaxies contained abundant gas, and many stars were born. Over cosmic time, the average rate of star formation has declined. This might seem to suggest that the best time for life has already passed. Many stars formed billions of years ago. Some older planets may have had plenty of time to develop life. Some may have existed before Earth was born. But star formation rate is only one part of the story. Early stars often had fewer heavy elements. Rocky planets needed cosmic enrichment. Also, the longest-lived stars remain available far into the future. Even if fewer new stars form later, many existing red dwarfs will continue shining for immense periods. The peak of star formation was not necessarily the peak of habitability. A bright young universe may have made many stars, but not all stars were equally suited for stable rocky worlds. Later cosmic time brought more metals, more mature galaxies, and many small stars with long lives ahead. The question becomes subtle. The universe may have formed many stars in the past, while still saving many life-friendly years for the future. The number of stars matters, but so does the kind of star, the chemistry of planets, and the time available for biology. The universe's busiest star-making days may be behind it, but its longest biological days may still lie ahead. Galaxies mature like slow gardens. A galaxy is not the same at every age. It begins with gas, dark matter, early stars, and growing structure. Over time, stars form, die, and enrich space. Spiral arms shape clouds. Supernovae stir gas. Heavy elements spread. Planets form around later stars. The galaxy becomes more chemically complex. This slow maturation matters for life. A young galaxy may be active and rich in star birth, but not yet chemically prepared for many rocky worlds. A mature galaxy may form fewer stars, but those stars may arise from richer material. Existing stars may also settle into long, stable lives. The Milky Way is a mature spiral galaxy. It has had time to build heavy elements. It contains older stars, younger stars, gas clouds, dust lanes, planets, and star-forming regions. The Sun formed after many generations of enrichment. If humanity is early, it is not early in the galaxy's first light. It is early in the possible span of life-friendly time. The galaxy has matured enough to make Earth, but it may continue offering habitable settings for far longer than Earth will exist. A garden can be old and still be early in its season. Some seeds may have already sprouted. Others may remain beneath the soil, waiting for future light. The Milky Way may already hold life. It may also hold worlds whose living chapters have not yet begun. The future universe will be darker, but not empty. Over very long timescales, the universe will change. Massive stars will vanish first. Sun-like stars will age and leave white dwarfs. Star formation will slow as gas is used up or locked away. The night sky of the far future will look different from today's sky, but darkness does not arrive all at once. Red dwarfs will keep shining for immense periods. White dwarfs will cool slowly. Planets may remain in orbit around long-lived stars. Some systems may stay stable for durations that dwarf the current age of the universe. If life can survive or begin in those settings, then the far future may still hold biology. It may not be biology around bright sun-like stars. It may be life around dim red stars, in underground oceans, in artificial habitats, or in forms that use energy carefully. This future is difficult to imagine because human experience is brief. 1 trillion years is not just longer than history. It is longer than the current universe by a vast margin. Yet some stars naturally live on such scales. The future universe may be quieter in visible light, but still rich in possibility. Its life, if it appears, may be slower, dimmer, and more patient. A darker future does not have to be a lifeless future. Some lamps are small enough to burn almost forever. White dwarfs may become future suns for close worlds. A white dwarf is the dense remnant of a sun-like star after it has shed its outer layers. It is small, hot at first, and slowly cooling over time. Around such an object, a habitable zone would be very close, because the white dwarf is faint compared with an ordinary star. The idea of life around white dwarfs is unusual. A planet would need to survive or arrive after the star's red giant phase. The earlier transformation may disturb or destroy inner planets, but material farther out can sometimes move inward later. In theory, a rocky planet could settle into a close orbit where temperatures allow liquid water for some period. This possibility is not simple. Tides, radiation history, atmospheric loss, and orbital stability all matter. A white dwarf system may be difficult for life, but it shows how habitability can appear in unexpected places and times. White dwarfs also have an observational advantage. Because they are small, a planet passing in front of one can block a relatively large amount of light. In principle, studying the atmosphere of such a planet might be easier than studying an Earth twin beside a bright sun-like star. No known white dwarf planet is confirmed to host life. The idea remains a carefully explored possibility. Even after a star's main life ends, a small circle of warmth may briefly remain. Brown dwarfs blur the line between stars and planets. Brown dwarfs are objects too massive to be ordinary planets, but not massive enough to shine like true stars through sustained hydrogen fusion. They glow faintly, mostly in infrared, and cool over time. They are sometimes called failed stars, though that phrase is more poetic than precise. Some scientists have considered whether planets or moons around brown dwarfs could have habitable conditions for limited periods. A young brown dwarf gives off heat, but as it cools, its habitable zone moves inward and changes. Stable long-term habitability may be difficult. Still, brown dwarfs expand the range of cosmic settings. They show that not every possible home must orbit a star like the Sun. Some worlds may receive heat from objects that are dim, cool, and hard to see. Others may be warmed internally, or by tides rather than by bright starlight. In the context of humanity being early, brown dwarfs matter because they remind science that future habitability may not follow one pattern. The universe's life-friendly places may include dim objects, hidden oceans, wandering planets, and small stars with long futures. Some possible homes may glow faintly, outside ordinary human expectations. A world does not need a noon sky to have a source of warmth. Rogue planets may carry hidden oceans through the dark. A rogue planet is a planet that does not orbit a star. It may have been thrown out of its original system by gravitational interactions, or it may have formed in isolation. Such a world drifts through interstellar space, without sunrise or seasons from a nearby sun. At first, a rogue planet seems like an unlikely place for life. Its surface would be cold and dark. Any surface ocean would likely freeze. Photosynthesis as Earth knows it would not be possible. But a rogue planet might still have internal heat. Radioactive decay, leftover heat from formation, and perhaps tidal heating from moons could warm its interior. If the planet has a thick atmosphere or a deep ice-covered ocean, liquid water might persist below the surface. This remains speculative. No known rogue planet is known to support life. But the idea matters because it widens the timeline and geography of habitability. Life-friendly environments may not all orbit bright stars. Some may drift quietly through darkness, invisible except through rare detection methods. If such hidden oceans can support biology, then the universe's living places may be far more difficult to count. Many could be dark, starless, and silent. A planet may wander without a sun and still keep a private warmth beneath ice. Interstellar space may contain more worlds than expected. As exoplanet searches improve, scientists learn that planetary systems can be dynamic. Young systems are crowded, bodies scatter one another, giant planets migrate, smaller worlds can be ejected. The galaxy may contain many free-floating planets, though their total number remains uncertain. These worlds are difficult to detect because they do not shine by reflected starlight from a nearby star. Some are found through gravitational microlensing, when their gravity briefly magnifies the light of a background star. Others may be detected through faint infrared glow if they are young and warm. If free-floating planets are numerous, then the universe contains many more worlds than the stars alone suggest. Most may be cold and lifeless. Some may have moons, some may keep subsurface oceans. Some may preserve chemistry across vast time. This does not make them likely homes for complex surface life. It does make them part of the wider question. The future of life may not belong only to bright planetary systems. It may include hidden habitats that are hard to see and hard to imagine. Humanity may be early in learning that planets are not always tied to suns. Some worlds may move through the galaxy like quiet seeds, carrying internal histories. A starless world can still be a world. The dark between stars may not be empty of places. Life may not need sunlight if it has chemistry. On Earth, sunlight powers most surface ecosystems. Plants, algae, and cyanobacteria use photosynthesis. They turn light into chemical energy and support much of the living world. But sunlight is not the only energy source life can use. Deep in Earth's oceans, hydrothermal vents support ecosystems based on chemical energy. Microbes use reactions involving minerals, water, and gases. Larger organisms depend on these microbial foundations. This matters for future and hidden life. A world without strong sunlight might still contain useful chemistry. An ocean beneath ice may have a rocky seafloor. Water-rock reactions may produce chemical energy. Hydrothermal activity may create gradients that life could use. If life can begin and persist in such environments, then many dark worlds become more interesting. Icy moons, rogue planets, and deep subsurface habitats may not be excluded from biology simply because they lack open sunlight. However, chemical energy may support different kinds of biospheres. Without sunlight, energy may be more limited. Life may remain microbial or slow-growing. Complex ecosystems may be possible in some cases, but technology would be unlikely in hidden oceans or buried environments. A world can be dark and still not be chemically still. In the absence of daylight, life may gather around the quiet warmth of rock. The universe may be full of slow life. Human life moves quickly. Plants grow in seasons. Animals breathe in moments. Civilizations rise across centuries. But life does not have to move at the same pace everywhere. In cold, dark, low-energy environments, biology may be extremely slow. On Earth, some microbes survive with very little energy. Deep beneath the seafloor, organisms can live at low metabolic rates. They may divide rarely, use energy slowly, and persist in environments that seem almost motionless from a human perspective. If many extraterrestrial habitats are cold, dark, or energy limited, then their life may also be slow. A biosphere under ice may change gradually. A rogue planet's ocean may evolve over enormous periods. A red dwarf world may have far more time than Earth, allowing slow processes to matter. Slow life would be difficult to detect. It may produce weak chemical signals. It may not transform a whole planet quickly. It may remain hidden in small pockets. Yet it would still be life. Its pace would belong to its environment. This adds another layer to the idea that humanity may be early. Some living worlds may already exist, but their evolution may move so slowly that intelligence, if it ever appears, lies far in their future. The universe may not be empty. It may be patient in ways that living things on Earth rarely need to be. Future life may be more common around small stars. Large stars live bright and brief lives. Sun-like stars live longer, but still have limited main sequence lifetimes. Small red dwarfs live longest of all. Because they are also common, they may dominate the future landscape of habitable possibilities. If red dwarf planets can support life, then future life may mostly orbit small stars. Such life may develop under redder light, close orbits, tidal locking, and long stable ages. Its skies may be different. Its photosynthesis, if it exists, may use different wavelengths. Its climates may be shaped by permanent day and night. This would make Earth's form of life only one chapter, not the universal pattern. Life around sun-like stars may be important early in cosmic history. Later, life around red dwarfs may become more important simply because those stars keep shining. The idea is not certain. Red dwarf habitability remains an active question, but the scale of time makes it powerful. Even a small chance of habitability around many long-lived stars creates an enormous future opportunity. Humanity may be early because it lives around a star that burns comparatively quickly. Many future biospheres, if they come, may arise under smaller suns long after the sun has changed. Earth's daylight may be one of the bright early versions of life's story. Later chapters may be written in dim red light. The search for life may eventually focus on patience. Modern astronomy often looks for what can be found now: transiting planets, nearby systems, atmospheres, signals, and solar system targets. This is natural. Science works with available instruments and reachable questions. But the deeper search may require patience across generations. Planets around red dwarfs may need long monitoring. Possible biosignatures may need repeated observations. Slow signals may need long-term archives. Future life cannot be detected today, but its possibility can shape how science understands cosmic time. Humanity may need to think like a long-lived civilization before it knows whether long-lived civilizations are common. This means preserving data, returning to targets, building observatories that can work for decades, and keeping questions alive beyond one lifetime. The idea is calming. The universe does not have to answer quickly. Some stars are only beginning their long lives. Some planets may still be waiting for stability. Some chemistry may still be gathering its first patterns. Some future minds, if they ever appear, may be billions of years away. The search for life is not only a search through space, It is a search through time, and time is the widest ocean of all. Part 3 of 9. The universe may still have many stars left to make. The night sky can make the universe feel complete, as if all its stars are already in place. But galaxies are not finished objects. They are slow, changing systems. Gas clouds still collapse. New stars still form. Some regions of the Milky Way continue to glow with young stellar nurseries. Star formation has slowed since the universe's earlier ages, but it has not stopped. Cold gas remains in galaxies. Clouds still gather under gravity. Stars are still born from dust and darkness. Around some of those future stars, planets may form. Around some planets, chemistry may settle into long and gentle stories. This means the universe's possible life-bearing worlds are not all present yet. Some have already formed, some may be forming now. Others may form millions or billions of years in the future. A civilization that does not exist today may belong to a world whose star has not yet been born. This changes the feeling of cosmic silence. The quiet sky may not only be a matter of distance, it may also be a matter of cosmic timing. Some of the universe's future living worlds may still be waiting inside clouds of gas. The universe is old, but creation has not ended. In dark nebulas and cold molecular clouds, future suns may still be gathering softly. Future planets may inherit richer chemistry. Every generation of stars changes the material from which later stars and planets form. Stars take simple elements and build heavier ones. They return these elements to space through winds, supernovae, and other endings. Over long ages, galaxies become more chemically enriched. This matters for planets. Rocky worlds need heavier elements. Atmospheres need oxygen, carbon, nitrogen, sulfur, and other ingredients. Life as Earth knows it depends on chemistry that the early universe did not have in abundance. Future planets may form from material that has been enriched by more generations of stars. Their birth clouds may contain more metals, dust, and complex molecules than the clouds of the early universe. This does not guarantee life. It only means the raw ingredients may be more widely available. There is a balance. Too many heavy elements can also influence planet formation in complicated ways. Giant planets may form more easily in metal-rich disks. Planetary systems can become crowded, dynamic, or unstable. Nature does not make habitability with one ingredient alone. Still, the larger pattern is gentle. The universe has spent billions of years preparing itself chemically. Earth formed after that preparation had already begun. Future worlds may inherit even more of that cosmic history. A planet born tomorrow, in cosmic terms, may be built from ashes of stars that have not yet died today. The universe keeps adding new words to the language of matter. The earliest habitable planets may not have been the easiest homes. Some planets older than Earth may have been capable of supporting life. The universe had stars and heavy elements before the sun was born. Rocky planets may have existed billions of years earlier. Some may have had water, atmospheres, and long histories of their own. But older does not automatically mean easier. Early galaxies were often more active. Star formation was stronger. Supernovae were more common in some regions. Heavy elements were still building up. Planetary systems may have formed under different conditions. A very old planet might have had enough time for life. It might also have faced stronger radiation environments, fewer stable ingredients, or more disturbances from nearby stellar activity. Some early worlds may have been promising. Others may have been difficult. This adds nuance to the idea that humanity is early. It does not mean Earth is the first living world. It means the universe's most life-friendly era may not be behind us. Many early worlds may have existed, but many future worlds may have better or longer opportunities. Habitability is not only about being first. It is about having enough stability, enough chemistry, and enough time. A planet born early may have time but less chemical richness. A planet born later may have richer material and a longer-lived star. The universe's first possible homes may have been real, but not always gentle. Later homes may inherit a calmer, richer dark. Galaxies may become quieter places with time. The early universe was more active than the present universe in many ways. Galaxies collided more often. Star formation was more intense. Massive stars lived and died quickly, producing energetic explosions. Black holes grew. Gas moved violently through forming structures. Over time, many galaxies become calmer. Their star formation slows, their structures settle. Violent events become less frequent in many regions. This does not make the universe still, but it may create more stable environments in some places. Stability matters for life. A planet can survive energetic events, but repeated disruptions may make complex biology harder. Nearby supernovae, strong radiation, close stellar encounters, and unstable orbits can all affect habitability. A quieter galactic environment may give planets longer peaceful intervals. The Milky Way is not perfectly safe or perfectly calm. It has supernovae, radiation sources, moving stars, and changing spiral arms. But Earth has enjoyed a long enough stable period for life to begin, survive, and become complex. Future planetary systems may also benefit from calmer conditions, especially in mature regions of galaxies. A quieter galaxy may allow slow biology, more room to unfold. The universe's younger ages may have been bright and energetic. Its later ages may offer more silence, and silence can sometimes be kind to life. Cosmic hazards may become less frequent in some future eras. Life on a planet can be influenced by events far beyond its surface. A nearby supernova could affect an atmosphere. A gamma-ray burst, if close and directed in the wrong way, could change upper atmospheric chemistry. Dense stellar environments can disturb orbits. A galaxy's history can shape a planet's long-term safety. These events are part of nature. They are not constant everywhere. Their frequency depends on star formation, galaxy type, location, and time. Massive stars, which create many energetic endings, live short lives. When star formation slows, some kinds of hazards may become less common. This means future planets in calmer galactic regions may have long stretches with fewer major cosmic disruptions. Such quiet intervals could matter for complex life. Microbes may survive many hardships, but large ecosystems and technological civilizations may benefit from long stability. No world is completely protected. Planets change from within, as well as from outside. Volcanoes, impacts, climate shifts, and biological changes all matter. But the wider cosmic environment is another layer of the story. If the universe becomes calmer in some ways, the future may offer gentler windows for life. Not brighter windows, perhaps. Not more dramatic ones, but longer, quieter ones. Sometimes the best environment for life is not the most energetic. It is the one that lets small changes continue for a very long time. The future may favor slow, stable worlds. Earth's life has always depended on balance. Too much change can erase habitats. Too little change can limit chemical renewal. Life grows best where energy flows, but not so violently that everything is constantly reset. The future universe may contain many worlds where change happens slowly. Planets around red dwarfs may have long orbits of stability after their early active phases. Icy moons may keep oceans for immense periods if tidal heating continues. Rogue planets may preserve hidden seas beneath thick ice. White dwarf planets, if they exist in stable orbits, may enjoy temporary windows of warmth. These worlds may not be bright or familiar. Some may be dim. Some may be cold on the surface. Some may hide their best environments underground. But they may have what life often needs: steady energy, chemistry, and time. Slow worlds may produce slow biospheres. A hidden ocean with limited chemical energy may not evolve quickly. A tidally locked planet may develop stable climate patterns over vast intervals. Life may remain microbial for ages, or gradually explore complexity under conditions very different from Earth's. Humanity may be early, because Earth's path was relatively quick compared with the future's longest possibilities. 4 billion years of life feels immense, but some future worlds may have far more time. The universe may still be preparing its slowest gardens. Their seasons may last longer than Earth's entire history. The longest-lived stars may have the most chances. A star's lifetime sets the outer rhythm for any surface planet that depends on its light. Massive stars are brilliant but brief. Sun-like stars offer billions of years. Red dwarfs may offer hundreds of billions or trillions. If life needs time, then long-lived stars may be important. A slow star gives chemistry more chances. It gives biology more time to adapt. It gives planets more opportunity to recover from difficult beginnings. It allows evolution to move patiently. But the relationship is not simple. A long-lived star is useful only if its planets can remain habitable. Red dwarf planets may face flares, tidal locking, and atmospheric loss. Some may be stripped bare. Some may freeze. Some may become too harsh. But if even a portion remains stable, their long lifetimes become meaningful. A short-lived star may host beautiful planets, but it may not give complex life enough time. A long-lived star may be faint, but its patience is enormous. The future universe will contain many such stars long after brighter ones have faded. This means the greatest number of life-friendly years may belong not to stars like the Sun, but to smaller, quieter stars. The brightest lamps do not always give life the longest story. Sometimes the dimmest stars are the ones with the most time to spare. Earth's timing may be unusual among living worlds. Earth orbits a yellow dwarf star during a relatively early period of the universe's long future. It formed after enough heavy elements existed, but before the long red dwarf era had truly unfolded. Its life appeared early enough to produce intelligence, while the universe is still bright with many star types. If most future life arises around red dwarfs, Earth may not be typical. It may be an early example of life around a sun-like star. Its bright days, blue sky, open oceans, and oxygen-rich air may belong to a particular chapter of cosmic history. This does not make Earth better or worse than future worlds. It only makes Earth specific. It has its own timing, its own star, its own moon, its own geology, and its own biological path. Other living worlds may be dimmer, slower, more hidden, or stranger. Humanity often imagines alien civilizations as older than Earth's. Some may be, if they exist, but many possible civilizations may be younger, or not yet born. Some may belong to stars that will still be shining long after the sun has changed. The question is not only whether humanity is alone, it is whether humanity belongs to an early wave of awareness in a universe with much more time ahead. Earth may be a morning world. Its questions may rise before much of the cosmic day has begun. Some future civilizations may never know the same sky. The night sky changes over cosmic time. Stars are born and die. Galaxies drift apart as the universe expands. In the very distant future, observers in some galaxies may see fewer other galaxies in their sky. The universe beyond their local group may fade beyond view. A future civilization may look upward and see a darker, emptier cosmos than humans see today. It may not easily discover the Big Bang from visible galaxies. It may not see the same cosmic web. It may live under a quieter, more isolated sky. This gives humanity a special moment. The universe is old enough to have galaxies, planets, heavy elements, and life. But it is young enough that distant galaxies remain visible. The cosmic microwave background can still be measured. The history of the universe can still be reconstructed. If humanity is early, it is early not only in biology, but also in cosmic visibility. The universe has not yet hidden much of its large-scale story beyond horizons. The sky still shows evidence of its origin and expansion. Future civilizations may have more time for life, but less access to some ancient clues. Their astronomy may be different. Their questions may have different starting points. Humanity may live during a rare era, when the universe can still be seen widely. The sky is not only beautiful, it is historically generous. The cosmic horizon makes some futures unknowable. The observable universe is limited by the speed of light and cosmic expansion. There are regions so far away that their light has not reached Earth. In the far future, expansion will carry many galaxies beyond observational reach. Their light will become too stretched and faint to see. This matters for future intelligence. A civilization born far in the future may be surrounded by a smaller visible universe. It may still study its own galaxy and nearby systems, but the grand evidence of cosmic expansion may be harder to find. For humanity, this means the present era offers a wide window. Telescopes can see galaxies billions of light years away. They can measure ancient light. They can study the early universe. They can learn that the Milky Way is only one galaxy among many. A future civilization may be more advanced biologically or technologically, yet have less direct evidence of the universe's earliest history. It may need to infer more from local clues. Some knowledge may become harder, not easier, with time. This adds a quiet poignancy to being early. Early observers see a universe that is still open in many directions. They may not have all the tools, but the light is still arriving. The present sky is a message from the deep past. One day, some of that message may pass beyond reach. Being early may be a responsibility. If humanity is among the early technological species, then its choices matter in a special way. It may not be entering a crowded galaxy full of ancient guidance. It may be learning how to be a civilization without many examples to follow. This thought is not meant to be heavy. It is a gentle reminder that awareness is rare in the known universe. Earth is the only confirmed living world. Humans are the only known species asking these questions with telescopes and spacecraft. If others exist, humanity has not yet heard them. If others will exist in the future, they are not here to guide the present. Earth's civilization must decide how to study, protect, explore, and listen with care. Being early would not mean being superior. It would mean being part of the universe's first known attempts to understand itself. It would mean that the search for life is not only about finding neighbors, it is also about becoming the kind of neighbor a living universe could trust. The silence of the sky can feel lonely, but it can also feel clarifying. It asks humanity to treat its world gently, because no replacement is known. It asks science to remain patient, because false certainty would be easy. A young voice in a quiet universe can still learn to speak softly. Part 4 of 9. The universe may have more future habitability than past habitability. When thinking about life in the universe, it is natural to look backward. The universe has existed for billions of years. Many stars are older than the sun. Some planets may have formed long before Earth. This makes humanity seem late, as if it arrived after a long cosmic silence. But time is not evenly spent. The past is only part of the universe's possible story. Many stars will continue shining for vast stretches ahead. Red dwarfs, especially, may provide stable light for periods far longer than the sun's lifetime. If their planets can remain habitable, then the future may contain more total opportunities for life than the past. This idea changes the shape of the question. Humanity may not be late, just because the universe is old. It may be early, if most life-friendly years still lie ahead. The present universe may be like a young forest, where some trees have already grown tall, while many seeds have not yet opened. Habitability depends on more than age. It depends on stars, planets, atmospheres, chemistry, geology, and stability. Many of these conditions may become more favorable, or at least remain available, across long future eras. The quiet sky may therefore not be a final statement. It may be a sign that much of the universe's biological potential still waits in time. The past has made life possible. The future may give it far longer to unfold. Earth may be early because it orbits a shorter-lived star. The sun is long-lived compared with human history, but not compared with the smallest stars. It will shine steadily for about 10 billion years on the main sequence. Earth has already used nearly half of that bright, stable chapter. Red dwarfs live far longer. Their light is dimmer, but their fuel lasts for immense spans. A planet around such a star, if it can keep an atmosphere and water, may have far more time than Earth. It may not be a perfect home. It may face tidal locking, flares, and atmospheric loss, but its star's lifetime gives it a long clock. This means Earth's timing may be unusual. Life here developed around a star that offers billions of years, but not trillions. Complex life appeared late in Earth's habitable window. Technological life appeared later still. If the same slow pattern happens elsewhere around longer-lived stars, many possible civilizations may not exist yet. A red dwarf planet could spend billions of years in early chemical stages. It could remain microbial for ages. It could wait for its star to calm. Its future may extend so far beyond Earth's that its biological story seems barely begun. The sun has given Earth a beautiful window, but not an endless one. Humanity may be early because it lives beneath a star with a shorter song. The first observers may not be the most common observers. If life and intelligence arise many times in the universe, the first civilizations may not represent the average civilization. They may appear around stars like the sun during a bright era of galaxies. While the universe is still rich with visible structure, later civilizations may arise under dimmer stars, in older galaxies, or in quieter regions. This creates a gentle distinction. Being early does not mean being first. It means belonging to an early part of a much longer distribution. A few worlds may awaken before most. A few minds may ask cosmic questions, while many future biospheres are still unformed. Earth could be one of these early observing worlds. It sees a universe still bright with galaxies. It can measure the cosmic microwave background. It can study star formation, exoplanets, and distant light. Future observers may have more time, but perhaps less access to some ancient cosmic evidence. The first observers may also shape how questions are asked. They may assume that silence means absence, when it may partly mean timing. They may look for older civilizations, not realizing that many future civilizations have not yet had their stars' long, quiet years. This idea makes cosmic loneliness softer. A quiet sky does not always mean no one will ever exist. It may mean few have arrived yet. The first lamps in a valley do not prove the valley will remain dark. They only show that evening has begun to glow. The universe's future may belong to dim stars. In the far future, the brightest and most massive stars will vanish first. They burn their fuel quickly and end their lives after relatively short cosmic times. Sun-like stars last longer, but they too eventually leave the main sequence. Red dwarfs remain, because red dwarfs are small and efficient. They can shine for extraordinary lengths of time. Long after the sun has become a white dwarf, many red dwarfs will still glow softly. They may become the main steady light sources of the far future. If planets around some of them are habitable, then future biology may happen under dim red light. Skies may look different. Days may not follow Earth's rhythm. Worlds may be tidally locked, with permanent day and night. Photosynthesis, if it appears, may use different wavelengths. Life may move slowly, shaped by low light and long stability. This would make Earth's bright blue world part of an earlier cosmic style. Future living worlds may not resemble it closely. They may be quieter, darker, closer to their stars, and far longer lived. The universe does not need to repeat Earth in order to make life. It may explore many kinds of living worlds across time. The future may not be as bright as the present, but it may have more years in which life can softly appear. Life around red dwarfs may begin after long delay. A red dwarf's early activity can be challenging. Flares and high-energy radiation may affect nearby planets. A young red dwarf may be more restless than an older one. For a close-orbiting planet, this early era could be difficult for surface water and atmosphere. But stars change. Many red dwarfs may calm as they age. If a planet keeps enough atmosphere, water, or subsurface reservoirs through its star's restless youth, it may enter a much longer stable period afterward. In that later period, habitability may become more possible. This creates a kind of delayed beginning. A planet may not become a good home immediately after formation. It may need to wait. Its early surface may be harsh, while its later climate becomes gentler. Its ocean may hide under ice until conditions change. Its chemistry may need long intervals of calm. Earth's own life did not require modern Earth to exist from the beginning. The planet changed. Its atmosphere changed. Its oceans changed. Life changed the planet in return. A red dwarf world may also have phases, each one opening or closing possibilities. If many future biospheres around red dwarfs are delayed, then the universe may seem quiet now, because many of those planets are not ready yet. Some worlds may not be lifeless. They may simply be waiting for their stars to settle. A long future does not guarantee life. The idea that humanity may be early is beautiful, but it must remain careful. More time does not automatically produce biology. A planet can have billions of years and still remain lifeless. It may lack water. It may lose its atmosphere. It may have the wrong chemistry. It may never cross the boundary from molecules to cells. Red dwarf planets especially remain uncertain. Some may lose water during their star's active early phases. Some may become airless. Some may be locked into climates too extreme for surface life. Some may have thick atmospheres that trap too much heat. Some may simply never develop living chemistry. The future may contain many possible years, but possibility is not proof. This is why science avoids turning hope into certainty. It studies actual planets, actual atmospheres, actual stars, and actual chemistry. It asks which worlds can truly remain habitable, not only which worlds have time. Still, time remains important. If even a small fraction of long-lived planets can support life, the future opportunity is enormous. A rare event can happen many times if the universe gives it enough places and enough years. The idea is not that life must fill the future. It is that the future gives life a vast and quiet chance. The first life may not be the first intelligence. A planet can become alive long before it becomes aware. Earth's history shows this clearly. Microbes appeared billions of years before animals. Animals appeared hundreds of millions of years before technology. Human civilization arrived in a tiny final moment. This means that even if life exists on many worlds today, intelligence may still be far in their future. A planet may already have microbes, but no complex cells. Another may have complex life, but no tool makers. Another may have intelligence, but no technology. Each stage can take a long time. If humanity is early, it may be early in the rise of intelligence, rather than early in the rise of life. The galaxy may already contain living worlds that are not yet visible as civilizations. Their biospheres may be quiet, slow and young. Their futures may still be unwritten. This possibility softens the silence. It allows the universe to be alive without being communicative. It allows Earth to be one of the first technological voices, while not being the only living place. It separates biology from astronomy's easiest signals. The question, "Where is everybody?" may skip over many worlds that are not ready to answer. A living planet may need billions of years before it can ask why the sky is silent. Complexity may require rare timing. Complex life depends on many layers. It needs an energy source, stable environments, useful chemistry, and enough time. It may also need oxygen, or another efficient metabolism. It may need ecological pressures that reward larger bodies, senses, movement, and cooperation. Earth took a long time to reach this stage. For most of its history, life was microscopic. Oxygen rose gradually. Complex cells appeared after a long delay. Animals appeared later. Land ecosystems developed later still. Intelligence capable of technology came at the end of a long and branching path. This suggests that even on living planets, complexity may not arrive quickly. It may depend on timing between geology, atmosphere, oceans, and evolution. A planet might have life but never enough oxygen. It might have oxygen but no path toward large organisms. It might have animals but no technological species. If many planets are still in earlier stages, the universe may be quiet because complexity has not had enough time to become common. The current age of the universe may be enough for Earth, but not necessarily enough for most possible living worlds. A few planets may develop quickly, others may move more slowly. Some may never move far beyond microbes. Complex life is not simply life made larger. It is a long conversation between a planet and its living chemistry. Oxygen-rich skies may be temporary windows. On Earth, oxygen is one of the great signs of life. It built up because of photosynthetic organisms and became part of the atmosphere's long story. Oxygen allowed larger, more active organisms to develop. It also created an atmospheric signature that might be visible from far away. But oxygen-rich atmospheres may not last forever. They depend on sources and sinks. Life produces oxygen, while rocks, volcanoes, weathering, and chemistry consume or transform it. A planet's atmosphere changes with time. A living world may only show strong oxygen during part of its history. This matters when searching for life across cosmic time. A planet may be alive before oxygen rises. It may be alive after oxygen declines. It may have life that never produces oxygen in large amounts. It may have oxygen produced through non-living processes. Every case needs context. If oxygen-rich skies are temporary, then many living worlds may be hard to detect during most of their histories. Earth itself would not always show the same biosignature. A telescope must look during the right planetary era. Humanity may be early not only because civilizations may come later, but because many biospheres may not yet have reached their most visible stages. A living planet may glow with evidence only during certain chapters. The challenge is to notice the chapter while it is open. Civilizations may arise after stars become quieter. A world star shapes its atmosphere, climate, and biological possibilities. If a star is very active early, a planet may face strong radiation and atmospheric changes. Later, if the star becomes calmer, the planet may have more stable conditions. For some worlds, civilization may not be possible until late in the star's life. Microbes might survive underground or underwater during harsh eras. Surface ecosystems might appear only when conditions soften. Complex life might follow much later. Technology might arrive after billions of years of preparation. This is especially relevant for red dwarfs because their lifetimes are so long. Their early active periods may be followed by vast quieter ages. If planets around them can keep water or recover habitability, then civilization may often be a late development. The present universe may be too early for many of these stories. Their stars may still be in youth. Their planets may still be settling. Their atmospheres may still be changing. Their life, if it exists, may be simple. A future astronomer around a quiet red dwarf might look back across time and wonder whether early sun-like civilizations ever existed. Earth might be one of those early lights, whether or not anyone ever knows it. Some worlds may need to wait not for life, but for calm. A civilization may be the flower of a very long season. The first civilizations may never meet each other. If technological civilizations are rare in time, the earliest ones may be widely separated. One may arise in one region of the galaxy, then fade or grow quiet before another appears nearby. A second may arise millions of years later, under another star. A third may not exist until much later still. This creates a lonely pattern. Early civilizations may be real, but isolated. They may not share the same era. They may look into the sky and hear no one, not because no one ever appears, but because few have appeared yet. The earliest civilizations may also lack guidance. They may not receive messages from older neighbors. They may not find obvious galactic structures. They may face the universe alone, at least for a while. Their loneliness would be a function of timing, not destiny. Humanity may be in this position. It may not be the first civilization, but it may be among the early ones in its region or era. If so, the quiet sky becomes less surprising. The galaxy's future conversation may not have begun in earnest. This thought is gentle. It turns cosmic loneliness into early arrival. A quiet house before dawn is not empty in the same way as an abandoned one. It may simply be waiting for others to wake. The first voices in a valley may call softly and hear only echoes. The silence may belong to the beginning, not the end. A universe with future life may still be lonely now. It is possible for two things to be true at once. The universe may eventually contain many living worlds, and the present sky may still be quiet. Future life does not comfort present loneliness in a simple way. A civilization that has not yet evolved cannot answer a signal today. This creates a deep kind of solitude. Humanity may belong to a universe rich with future potential, but poor in current neighbors. It may be surrounded not by absence, but by beginnings too early to speak. The galaxy may be filled with planets that are not yet alive, living worlds that are not yet complex, and complex worlds that are not yet technological. This idea gives the silence a tender quality. The universe is not necessarily indifferent. It may be unfinished. Its future may contain many minds, but the present may hold only a few. A young intelligence may therefore feel alone, even in a universe that will not always be lonely. The feeling is similar to standing in a vast garden before spring. The ground is quiet, the air is still. Nothing obvious has bloomed. Yet beneath the surface, time is preparing many things. A lonely present does not prove an empty future. Sometimes silence is the sound of life not yet begun. The future may never know humanity existed. If humanity is early, many future civilizations may arise long after Earth has changed beyond recognition. The sun will eventually become brighter, altering Earth's climate. Far later, it will leave the main sequence. The planet's surface will not remain as it is today. Human artifacts may not last forever. Radio signals weaken as they spread. Spacecraft drift, but they are small. Geological processes erase many traces. Over immense time, evidence of humanity may become fragile. A future civilization around another star may never know Earth existed. It may look into the sky and ask its own version of the question. It may wonder why the universe seems quiet. It may search for earlier minds and find no clear trace. This possibility is not sad in a loud way. It is part of cosmic scale. Most things do not last forever. Stars, planets, civilizations, and messages all belong to time. Yet the act of existing still matters. A flower matters, even if no distant future eye sees it. Humanity's questions, music, science, and care belong to this moment. They are real because they happen, not because they are permanent. An early civilization may never be found by later ones. Still, for a while, the universe became aware here and looked outward. Preserving knowledge is a way to speak to the future. If humanity is early, then preservation becomes meaningful. Records, spacecraft, archives, science, and stories can carry information forward. They may not last forever, but they extend memory beyond one lifetime. The Voyager Golden Records are small examples. They carry sounds and images of Earth into interstellar space. Their chance of being found is extremely small, but their meaning is symbolic. They say that a living world existed here, with music, language, nature, and curiosity. On Earth, preserving knowledge also matters. Scientific records allow future generations to continue questions. Astronomical data can be reanalyzed. Fossils, ice cores, rocks, and observatory archives become messages across time. A civilization speaks to its own future before it speaks to the stars. A long-lived search for life requires continuity. One generation cannot answer everything. It can leave tools, methods, questions, and care for the next. This is how slow mysteries are approached. The universe may be too large for one lifetime, but not too large for a chain of minds. Each mind holds the question briefly, then passes it on. To preserve knowledge is to make a small bridge across time. In a quiet universe, memory itself becomes a form of light. The search for future life begins with caring for present life. Speculating about future civilizations can make the universe feel vast and abstract. But the only known life is here. Earth is the only confirmed biosphere, and humanity is the only known technological species. This gives the present world a special weight. If humanity is early, then Earth's survival matters even more. It may be one of the universe's first known experiments in self-aware life. Its ecosystems, cultures, languages, and sciences are not replaceable in any confirmed cosmic sense. They are not one example among many known examples. They are the only known example. The search for life beyond Earth does not reduce Earth's importance. It increases it. Every exoplanet studied, every icy moon imagined, and every possible future biosphere reflects back on the living planet that asks the question. A civilization that hopes to meet future neighbors must first learn to remain a good home for itself. Patience, care, and curiosity are not separate from survival. They are part of the same long story. The future universe may contain many living worlds, or very few. Either way, Earth matters now. A small blue planet is not less precious because the future is large. It is the first known place where the future can be imagined. The early universe made atoms, but not meaning. The early universe was full of physics. Particles formed, atoms gathered, gravity shaped matter, and stars began to shine. But meaning, as living minds know it, required much more. It required planets. It required chemistry. It required life. It required organisms that could feel, remember, and ask. This does not mean the universe had no beauty before life. It was beautiful in structure, light, and law. But beauty needed observers to be experienced. Questions needed minds. Meaning, in the human sense, appeared only when matter became aware. If humanity is early, then meaning itself may be early. The universe may have had stars for billions of years before it had many beings capable of wondering about them. It may still be near the beginning of its age of observers. This thought gives a quiet dignity to consciousness. A mind is not separate from the cosmos. It is one of the ways the cosmos becomes known. When a human looks at the stars, atoms made in stars are studying starlight. Future minds may do the same under different skies. They may ask different questions, use different senses, and build different sciences. But the act will rhyme with this one. The universe spent billions of years becoming visible. Life made it meaningful to be seen. Part 5 of 9 future civilizations may arise under unfamiliar skies. If humanity is early, then many future civilizations may not look back at skies like Earth's. They may not live under a yellow-white sun. They may not know blue daylight, familiar seasons, or a large pale moon. Their worlds may orbit red dwarf stars, white dwarfs, or other long-lived sources of warmth. A civilization around a red dwarf may see a star that appears larger and redder in the sky, if the planet orbits close enough for warmth. If the planet is tidally locked, the star may hang almost still over one side of the world. The night side may remain dark, while a twilight region circles the planet like a permanent evening. Such a civilization would build its sense of time differently. Without normal sunrises and sunsets, it may use tides, weather, biology, or artificial clocks. Its calendars may follow orbital motion, climate cycles, or the rhythms of its star's activity. Its myths, sciences, and instruments would grow from a sky unlike Earth's. Future intelligent life may therefore ask familiar questions from unfamiliar places. It may wonder about the stars. It may search for neighbors. It may study atmospheres, planets, and ancient light. But its starting point may be very different from humanity's. Cosmic curiosity does not require an Earth-like sky. A mind can awaken beneath red light, and still wonder why the universe is quiet. A planet's sky shapes how it understands the universe. Earth's sky has guided human thought for thousands of years. The daily rising of the sun, the phases of the moon, the motion of planets, the turning of constellations, and the darkness between stars all shaped early astronomy. The sky became a calendar, a compass, a storybook, and later, a scientific instrument. Another world's sky may teach different lessons. A planet with thick clouds may rarely see stars from its surface. A civilization there might discover astronomy late, after learning to fly above the clouds or send instruments into space. A world around a red dwarf may have a dimmer sky and different colors of light. A moon around a giant planet may see a huge world hanging above its horizon. A tidally locked world may not have a normal day-night cycle. If one side always faces the star, the movement of shadows may be subtle or absent. The stars may be visible only from the night side. The border between day and night may become the natural place where light and darkness meet. These differences matter. Science is universal, but the path towards science may depend on environment. Some worlds may make astronomy easy. Others may hide the stars for a long time. Humanity's curiosity grew beneath an open sky. Future minds may need to climb through clouds, ice, or darkness before they see the wider universe. Cloudy worlds may delay astronomy. A planet can be habitable and still hide the stars. Thick clouds can cover a sky for long periods. Venus shows how a rocky world can be wrapped in bright clouds, though its surface is not friendly to Earth-like life. Other planets may have thick water clouds, hazes, or atmospheric layers that block a clear view of space. If intelligent life evolved on a cloudy world, its early astronomy might be very different. It may know weather, light, and shadow, but not stars. It may measure time through biological rhythms, tides, or subtle changes in the atmosphere. The universe beyond the clouds may remain unknown until technology rises high enough. This could delay the search for other worlds. A species that cannot see the stars may not build astronomy early. It may still develop mathematics, biology, chemistry, and engineering, but its cosmic awareness may come later. It may not ask whether it is alone until it can see that there are other suns. Earth's relatively clear sky helped humans notice patterns. Ancient observers tracked planets, eclipses, seasons, and constellations. This did not make science inevitable, but it gave curiosity a visible stage. A cloudy living world may be rich with life, culture, and thought, yet late in discovering the universe. Sometimes the stars are not absent. They are simply hidden behind a soft ceiling of air. Ocean worlds may produce intelligence without astronomy. An ocean world may be alive, complex, and even intelligent, while still remaining isolated from the sky. If life evolves beneath a global ocean, especially under ice, it may never see stars directly. Its environment may be dark, pressurized, and shaped by currents, chemistry, tides, and heat from within. Such a world could support senses very different from human senses. Creatures may understand pressure, sound, electric fields, chemistry, or vibration with great sensitivity. They may build complex social systems. They may remember, communicate, and adapt. Yet astronomy may be nearly impossible from within their natural environment. A species in a deep ocean may not discover fire. It may not develop metallurgy in the same way land species can. It may lack access to open air, dry surfaces, and visible stars. Technology, if it develops, may take a very different route. It might never become detectable across space. This matters for the idea that humanity may be early. The future universe may contain many intelligent beings that do not become astronomical. Some may be hidden, not by time, but by environment. Others may become aware very slowly, if at all, of the cosmos beyond their ocean. A world can contain minds and still have no night sky. In a dark sea beneath ice, intelligence may never learn that stars exist. Surface life may be only one version of biology. Earth's surface is full of life, so surface life feels natural. Forests grow under sunlight. Animals move across land. Birds cross the air. Humans look upward from open ground and build observatories beneath the sky. But many possible habitats are not surface habitats. Mars may have protected environments underground. Europa and Enceladus may have oceans beneath ice. Rogue planets may hold internal seas. Some exoplanets may have deep atmospheres, thick clouds, or high-pressure oceans where the most stable environments lie below. If most life in the universe lives below surfaces, then most life may be difficult to detect. It may not create strong atmospheric signs. It may not see the stars. It may not build technology that communicates through space. Its biology may be real, but hidden. Earth itself contains deep life. Microbes live underground and beneath the seafloor. They use slow chemical energy. They do not depend directly on sunlight. They show that a biosphere can extend into places that seem still and dark from above. Surface civilizations like humanity may therefore be unusual. They have direct access to sky, land, fire, weather, and visible stars. That combination may be especially helpful for astronomy and technology. A planet's surface can become a window. Many living worlds may have their windows closed. Fire may be an important step toward technology. Human technology depends deeply on fire. Fire cooked food, changed materials, hardened tools, provided warmth, produced light, and eventually led toward metallurgy, engines, and industry. It made chemical energy visible and controllable. Fire requires certain conditions. It needs fuel, oxygen, or another oxidizer, and an environment where combustion can occur. Underwater, fire is extremely difficult. On a world without enough atmospheric oxygen, ordinary fire may not exist. On a world with no dry land, there may be no simple path from intelligence to flames. This could matter across the universe. A planet may have intelligent life, but no fire. Without fire, certain technologies may be delayed or impossible. Metalworking may be difficult. Ceramics, glass, engines, and many energy systems may follow different paths or never appear. Earth's atmosphere became oxygen-rich because of life. Later, that oxygen allowed fire to exist in a familiar way. In this sense, biology prepared the environment for technology. Life changed the sky, and the changed sky allowed a technological species to emerge. If oxygen-rich atmospheres are rare or temporary, fire-based technology may also be rare. Intelligence may arise many times, but not always find the chemical doorway to industry. A small flame on Earth may represent a very unusual bridge between life and the stars. Metalworking may require land, fire, and accessible minerals. Technology is not built from intelligence alone. It also needs materials. On Earth, humans used stone, bone, wood, clay, copper, bronze, iron, and many other substances. These materials were accessible on land. They could be shaped, heated, combined, and passed through generations of craft. A world without land may make this harder. An ocean civilization may have minerals below, but not dry fire. A planet with thick ice may hide rock beneath kilometers of water or frozen crust. A cloud-covered world may have surface resources, but discover astronomy late. A world with abundant life but little accessible metal may develop along a different path. This suggests that the route to radio telescopes may be narrow. A species needs not only intelligence, but also hands or manipulators, social learning, stable memory, accessible resources, energy sources, and environments where tools can accumulate. Earth provided many of these conditions. It had land and sea, oxygen and fire, metals and stone, wood and clay, stable climates and changing challenges. Human technology grew from a planet that offered both opportunity and pressure. Future civilizations may arise in places where some ingredients are missing. They may become wise without becoming industrial. They may become social without becoming astronomical. Between a clever mind and a telescope, there are many quiet materials. Language and memory may need long, stable cultures. A technological civilization depends on knowledge that survives individuals. One mind can discover, but a civilization must remember. Language, teaching, symbols, tools, writing, and later digital storage allow knowledge to accumulate across generations. This accumulation may require stability. A species may be intelligent but live in conditions where long-term preservation is difficult. It may lack durable surfaces for writing. It may live underwater, where fire and paper are absent. It may have short lifespans, solitary habits, or unstable habitats that interrupt cultural memory. On Earth, human knowledge grew through speech, tools, art, markings, writing, mathematics, printing, instruments, and computers. Each layer made later layers possible. Astronomy depended not only on eyes, but on records. By comparing observations across time, people learned that the sky had patterns. A future intelligent species may need similar continuity, though not the same methods. It may store memory chemically, acoustically, biologically, or through structures unfamiliar to humans. But it must preserve information somehow, if it is to build science. This adds another reason cosmic intelligence may be delayed. Biology may produce clever animals often, but durable cumulative culture may be less common. A civilization begins when memory becomes larger than one life. Across time, knowledge is a small flame passed from hand to hand. Agriculture may not have an alien equivalent. On Earth, agriculture changed human history. It allowed larger settlements, stored food, population growth, specialized labor, cities, writing, trade, and eventually scientific institutions. It was not the only important step, but it helped create the conditions for complex civilization. Alien life may not follow this pattern. A world may have intelligent hunters or gatherers without domesticable plants or animals. An ocean species may not farm in the same way. A planet with unstable climates may not support long-term cultivation. A biosphere may lack organisms that can be easily domesticated. Without agriculture or something similar, technological development may be slower or different. A species can be intelligent without cities. It can have culture without industry. It can understand its environment deeply without building telescopes. This does not mean agriculture is required everywhere. Another world may have different paths. Perhaps it farms microbes, manages reefs, cultivates chemical gardens, or uses symbiosis in unfamiliar ways. The general principle is stored energy and stable communities, not wheat fields exactly. Still, Earth's route to technology depended on specific ecological opportunities. The planet offered plants and animals that could be domesticated, climates where farming worked, and landscapes where settlements could grow. Civilization may require not only intelligence, but a living world that can be shaped gently enough to support it. Planets may produce many cultures before one becomes technological. Human history did not move directly from intelligence to science. It passed through many cultures, languages, environments, migrations, discoveries, and ways of living. Some societies built cities, others lived in smaller groups. Some focused on farming, trade, craft, navigation, astronomy, or philosophy. Many different paths shaped the final technological world. An alien planet, if it has intelligent life, may also produce many cultures. Some may never develop large-scale technology. Some may value balance over expansion. Some may live in environments where technology is not useful in the same way. Some may rise and fade before they discover astronomy. This means a planet can have intelligence for a long time before it becomes detectable. It may pass through many quiet ages. Its beings may sing, build, remember, and wonder locally, without sending anything into space. From Earth, such a planet would appear silent. If humanity is early, future civilizations may also spend long stretches in pre-technological stages. Their intelligence may already exist, or may one day exist, but the moment of radio or spaceflight may be brief and late. The universe may contain many worlds with stories, but no signals. A culture can be rich beneath its sky and still leave no mark between stars. Technology may depend on accidents as much as intelligence. Many discoveries on Earth depended on specific circumstances. Fire was available, metals could be smelted, the atmosphere allowed combustion, useful plants and animals existed, the moon shaped tides, continents shifted, climate changed, extinctions opened ecological space, human anatomy allowed tool use and speech. Some of these conditions may have been necessary, others may have simply helped, but together they formed a path that led to technology. A different planet might produce intelligent life, but lack some of these accidents. Its path could pause, turn inward, or never become visible. This makes technology seem less inevitable. Evolution does not aim for radio telescopes. A world may have clever organisms for millions of years without industrial science. Even on Earth, modern technology appeared only once, very recently. If future civilizations are rare, the reason may not be that intelligence is rare. It may be that the combination of intelligence, environment, materials, culture, and chance is rare. Humanity may be early, because Earth's particular accidents align sooner than many others. Or humanity may be rare because those accidents seldom align at all. A telescope is not only a machine, it is the final shape of countless small coincidences across deep time. Future civilizations may inherit different cosmic evidence. Humanity studies the universe during a time when many kinds of evidence are available. Distant galaxies can still be observed. The cosmic microwave background can still be measured. Star formation is still active. The Milky Way is rich with many kinds of stars. Supernovae, exoplanets, nebulae, and cosmic structure are all visible. In the far future, some evidence may be harder to find. Cosmic expansion will carry distant galaxies beyond view. The microwave background will become colder and more stretched. Star formation will decline. The visible universe may appear quieter. A future civilization may still become scientific. It may study local stars, planets, physics, and its own galaxy. But reconstructing the universe's earliest history may be more difficult. It may not see the same wide cosmic landscape humans can observe today. This makes humanity's timing special. It may be early enough to see the universe's ancient light clearly, yet late enough for planets, chemistry, and life to exist. That combination may not last forever. The present era is not just a time for life. It is a time when life can see far into the universe's past. The search for other minds may be easier now than later. Today, the universe is still bright with many star types. Galaxies are visible across great distances. Stars like the sun still shine. Red dwarfs shine too. Exoplanet systems can be studied. The sky contains both young and old objects, offering rich comparisons. In the far future, some kinds of searches may become harder. There may be fewer bright young stars. Fewer nearby civilizations may overlap in time. Expanding space may hide distant galaxies. Signals from faraway regions may become weaker or impossible to receive. This does not mean future civilizations cannot search. They may have extraordinary technology. They may study local worlds deeply. They may preserve knowledge for long ages. But the cosmic landscape available to them may be different. Humanity's era may therefore be valuable for listening and looking. If there are civilizations now, this is the time to search for them. If there are none nearby, the search still builds knowledge for the future. It creates records, methods, and questions that later minds may inherit. Being early can mean having a wider sky, even without older neighbors. The silence around Earth may be lonely, but the view is still generous. A young civilization may mistake early silence for permanent silence. If a civilization begins listening early in cosmic history, it may hear little. It may search nearby stars and find no signals. It may look at planets and find no obvious biospheres. It may wonder whether it is alone. But the silence it hears may be temporary. Other civilizations may not yet have appeared. Living worlds may still be simple. Red dwarf biospheres may still be in their early stages. Planets may still be waiting for stable conditions. This does not mean silence should be ignored. It carries information. It tells what has not been found yet. But early silence should not be mistaken for eternal silence. A quiet morning does not prove the whole day will remain quiet. Humanity may be in such a morning. Its instruments are new. Its search is brief. Its knowledge of exoplanets is young. Its understanding of habitability is still growing. The galaxy's future remains far longer than its past in some important ways. The careful response is to keep listening without forcing an answer. The universe may be empty of nearby civilizations, or simply early in its larger biological history. A young listener must learn the difference between silence and waiting. The future may contain answers Earth will never hear. If civilizations arise far in the future, Earth may not be there to listen. The sun will change. Earth's surface habitability will end long before the universe's longest-lived stars fade. Humanity's current form may not last into the deep future. No one knows what descendants, records, or traces may remain. This means some answers to the question of life may be forever beyond Earth's direct experience. Future minds may discover other civilizations. They may find living worlds. They may build a galactic community, or they may also find silence. Earth may never know. This is humbling, but also peaceful. Not every answer belongs to the present. Some questions are larger than the beings who first ask them. Science is a chain, and the chain may extend beyond one species, one planet, or one era. Humanity's role may be to begin the question carefully, to search honestly, to preserve knowledge, to care for the only known living world, to leave records for whatever future may follow. A question can matter even if its final answer arrives after the questioner is gone. The stars teach that meaning does not require possession. Some worlds may become habitable only after long transformation. A planet's first state is not always its final state. Earth changed dramatically across time. Its atmosphere transformed, continents shifted, oceans changed chemistry. Life altered air, rock, and climate. The planet became more suitable for complex life through its own evolving systems. Other worlds may also transform. A planet may begin frozen and later warm. It may begin with a thick atmosphere and later lose part of it. It may gain stability after impacts decline. It may develop oceans after internal heat, volcanism, or atmospheric changes reshape its surface. This means some future habitable worlds may not be habitable now. They may need long planetary evolution before life can begin or thrive. A red dwarf planet may need its star to calm. A moon may need tidal heating to stabilize. A planet around a white dwarf may need to settle into a new orbit after stellar change. Habitability is not always a fixed address. It can be a chapter in a planet's life. Some worlds may have missed their chapter. Others may still be approaching it. The universe may hold many planets that are not ready yet, but not hopeless. A world can be a seed long before it becomes a garden. The idea that humanity is early makes the silence gentler. Cosmic silence can feel lonely when it is imagined as emptiness. But if humanity is early, the silence changes. It becomes less like an abandoned universe and more like a quiet beginning. The stars are not necessarily empty. Many possible stories may simply be unfinished. This idea does not claim certainty. It does not prove life will be common. It does not prove future civilizations will appear. It is only one careful possibility, shaped by long-lived stars, future habitability, and the slow pace of biological evolution. Still, it offers a calm way to hold the mystery. The universe may be silent because it is still young in the ways that matter for life. Earth may be one of the first places where a planet learned to ask about other planets. Humanity may be part of the early dawn of awareness. If so, the silence is not only a question, it is a responsibility. Early voices must learn patience. Early observers must learn humility. Early civilizations must learn to care for the rare light they carry. The universe may not be lonely forever. For now, it is quiet enough for wonder to be heard. Part 6 of 9 Earth's habitable window is not endless. Earth feels stable because human lives are brief. Oceans remain, clouds move, seasons return. The sun rises with familiar warmth. But across geological time, Earth's future is limited by the slow brightening of the sun. As the sun ages, it gradually becomes more luminous. This happens slowly, over hundreds of millions and billions of years. More sunlight means more heat entering Earth's climate system. Eventually, this will challenge the balance that has kept liquid water on the surface for so long. Long before the sun becomes a red giant, Earth's surface may become much less friendly to complex life. Weathering, carbon dioxide, oceans, and atmospheric chemistry will change. The biosphere may retreat, simplify, or fade from the surface. Earth's living chapter is long, but it is still a chapter. This gives another meaning to being early. Humanity appears during a narrow period when Earth has complex life, oxygen-rich air, visible stars, and technology. Earlier Earth was alive, but not technological. Later Earth may no longer support the same kind of biosphere. A living world is not only a place, it is a time. Earth's present is a rare, quiet interval between ancient chemistry and distant change. The sun will not remain the same forever. Stars like the sun spend most of their lives fusing hydrogen into helium in their cores. This stage is called the main sequence. It is long and steady compared with human time, but it does not last forever. Eventually the core changes, the outer layers expand, and the star becomes a red giant. For Earth, this future lies far away. It is not part of ordinary human time, but in the long story of habitability, it matters. The sun's changing life sets an upper limit on Earth's surface conditions. The same is true for planets around other stars. A star's evolution shapes the lifetime of its worlds. Sun-like stars may offer billions of years, enough for life to begin and become complex in at least one known case. But smaller red dwarfs may offer much longer stable periods. If their planets can remain habitable, they may have futures that stretch far beyond Earth's window. This does not make the sun a poor star. It gave Earth enough time for oceans, microbes, forests, animals, and mines. But it is not the longest clock in the cosmos. Humanity lives beneath a generous star, not an eternal one. A brighter future for the sun means a shorter future for Earth's surface life. Venus may show one path a rocky world can take. Venus and Earth are similar in size, but their surfaces are profoundly different. Earth has oceans, moderate temperatures, and a breathable atmosphere for its life. Venus is wrapped in a dense carbon dioxide atmosphere and bright clouds. Its surface is extremely hot. Venus is not simply Earth's twin. It is a lesson in planetary divergence. Two rocky worlds can begin with some similarities and follow very different paths. Atmosphere, distance from the sun, water, geology, and climate feedbacks all shape the outcome. For Earth's future, Venus is sometimes used as a reminder that habitability is a balance. A planet can lose surface water. Greenhouse warming can change the character of a world. Atmospheres can become dense, dry, or chemically transformed. The comparison matters for distant exoplanets too. A planet near Earth's size is not automatically Earth-like. It may be more like Venus, or Mars, or something unfamiliar. To know whether a world is habitable, science must study its atmosphere, temperature, star, orbit, and history. If humanity is early, it may also be living during Earth's most generous phase, not the beginning of Earth, and not the end, but a middle moment when complex life can look outward. A planet's kindness may be temporary, even when the planet itself endures. The future of Earth may become quiet again. For most of Earth's history, the planet was not filled with visible animals, cities, or machines. Microbes dominated for billions of years. Later, complex life flourished. Much later still, intelligence began to study the stars. In the far future, Earth may become simpler again. As the sun brightens and conditions change, complex surface life may become harder to sustain. The biosphere may shrink into protected environments. Microbes may outlast many larger forms, as they have endured many changes before. This possibility gives Earth's present a delicate feeling. The planet's technological age is not only brief compared with the past, it may also be brief compared with the future. A distant observer would need to look during a narrow window to detect human technology. The same may be true elsewhere. A planet may be visible as technological for only a small fraction of its life. Before that, it may be alive but quiet. After that, it may become quiet again. This helps explain why civilizations may be hard to find, even if they occur. A world may shine with intelligence for a short moment between two long silences. Earth's present voice is small, bright, and temporary. A civilization may need to outgrow its first planet. If a technological species lasts long enough, it may eventually face the limits of its home world. Stars evolve, planets change, climates shift, impacts geology, and biological changes continue. A civilization that remains only on one planet may be tied to that planet's future. This does not mean expansion must be loud or careless. It can be thoughtful, slow, and protective. A civilization may send instruments first. It may build habitats nearby. It may preserve life, knowledge, and culture in more than one place. It may learn to live beyond its birthplace without forgetting it. Humanity has only begun this possibility. Spacecraft have explored the solar system. Small human outposts have existed in orbit. Robotic missions have visited planets, moons, asteroids, and comets. These are early steps, not a settled future. If humanity is early, then it may also be early in learning how civilizations survive over cosmic time. Future civilizations may face similar questions. How does a living world protect its knowledge? How does it explore without harm? How does it carry life carefully into wider space? A planet may give birth to awareness, but the stars ask whether awareness can endure. The first home remains precious, even if the future grows larger. Life may spread naturally between nearby worlds. Panspermia is the idea that life, or the ingredients of life, may move between worlds. Impacts can blast rocks from a planet into space. Some of those rocks can travel for long periods and eventually land elsewhere. Meteorites from Mars have reached Earth, showing that material exchange between planets is real. Whether living microbes can survive such journeys is uncertain. Some Earth organisms can endure cold, dryness, and radiation for surprising lengths of time, especially when protected. But interplanetary travel is difficult. Space is harsh, and time can be long. Even if living cells rarely survive, organic molecules can travel. Meteorites, comets, and dust can carry carbon-rich chemistry. Young planets may receive ingredients from many places. In this gentler sense, worlds share material all the time. For the idea that humanity is early, panspermia adds a quiet layer. If life can spread naturally, then early living worlds might seed later ones. Biology may not always begin separately. It may sometimes travel in fragments of stone, ice, and dust. Earth may be part of a larger exchange of matter, even if no living transfer has been proven. Between planets, a rock can become a quiet carrier of possibility. Future life may be seeded by earlier life. If life ever spreads between worlds, whether naturally or intentionally, then early biospheres could influence later ones. A living planet might send microbes outward through impacts. A civilization might one day preserve or carry life to places where it can survive. Future habitats might contain descendants of earlier ecosystems. This idea must be treated carefully. Moving life to another world raises deep questions. If a planet already has native life, introducing Earth life could confuse or harm its history. Planetary protection exists because untouched worlds matter. Their chemistry and possible biology should be studied respectfully. But in the very long future, the preservation of life may become part of cosmic history. If Earth's surface becomes less habitable, life may continue elsewhere only if it spreads. This could happen through technology, or perhaps through natural processes under rare conditions. A universe where humanity is early may be a universe where early life shapes future life, not by conquering the stars, but by carrying the fragile pattern of biology beyond one world. The thought is quiet and profound. A cell, a seed, or a stored genome could become a bridge between eras. Life may survive time by learning how to travel gently. The search for future life includes the search for future homes. Astrobiology often looks for life that already exists. It studies Mars, icy moons, exoplanets, atmospheres, and biosignatures. But the same science also reveals places that may become important later. Some worlds are not habitable now, but they teach how habitability works. Mars is cold and dry today, but it preserves a record of ancient water. Europa and Enceladus may have hidden oceans. Titan has complex chemistry. The Moon preserves history on its surface. Asteroids carry materials from the early solar system. Each place teaches part of the story. Future homes for life may not be perfect copies of Earth. They may be artificial habitats, protected environments, underground spaces, orbiting stations, or carefully managed worlds. A long-lived civilization may learn that habitability can be created as well as found. This does not reduce the wonder of natural living worlds. It expands the meaning of life's future. Biology may begin on planets, but intelligence may eventually build shelters beyond planetary surfaces. If humanity is early, then the future of life may depend partly on whether early intelligence learns to understand habitability deeply enough to preserve it. A home is not only discovered, sometimes with patience and care, it is made. Terraforming is a dream of changing worlds. Terraforming means altering a planet or moon to make it more Earth-like, or at least more habitable for Earth life. The idea often appears in science fiction, especially with Mars. It imagines thickening atmospheres, warming climates, releasing gases, or creating conditions where liquid water could last. In reality, terraforming is far beyond current ability. It would require enormous energy, deep knowledge, long timescales, and careful ethics. Mars, for example, does not appear to have enough easily available carbon dioxide to simply create an Earth-like atmosphere with known methods. Its low gravity and lack of a global magnetic field add further complications. Still, the idea matters because it shows how future civilizations might think about habitability. They may not only search for ready-made Earths, they may also learn to build protected environments, restore damaged ecosystems, or create small habitable regions in otherwise difficult places. The most realistic early steps may not be planet-wide transformation. They may be enclosed habitats, underground shelters, greenhouses, and local ecosystems. These would be small islands of life, not new Earths. Terraforming remains speculative, but the underlying question is real. Can intelligence become a caretaker of environments, rather than only a product of them? A future garden on another world may begin under glass, with one carefully protected breath. Artificial habitats may outlast planets. A civilization does not necessarily need to live only on planetary surfaces. It might build habitats in orbit, inside asteroids, near moons, or between planets. These habitats could be designed to provide air, pressure, warmth, water, and ecosystems. Artificial habitats are challenging, but they offer flexibility. They can be placed where resources exist. They can be built slowly. They can use sunlight, nuclear energy, or other power sources. They can rotate to provide artificial gravity. In principle, they can preserve life even when natural planetary surfaces are limited. In the very long future, artificial habitats may become important for survival. A species around a changing star might move outward. It might live inside structures rather than on planets. It might preserve ecosystems in carefully managed spaces. This possibility changes the search for future civilizations. Advanced life may not always be tied to Earth-like planets. It may live in many small habitats spread across a system. Such habitats might be difficult to see from far away, unless they create noticeable heat, light, or patterns. The future of life may be both natural and constructed. Oceans, forests, and cells may one day share the cosmos with careful artificial gardens. A living world can begin as a planet and continue as many quiet homes. O'Neill cylinders imagine cities in space. One proposed kind of space habitat is the O'Neill cylinder. It is a large rotating structure that could create artificial gravity through spin. Inside, people imagine landscapes, air, water, sunlight reflected by mirrors, and closed ecosystems. No such large habitat exists today. The idea remains far beyond current construction, but it gives a concrete shape to the possibility that life could live away from planets. A civilization with enough engineering skill might build rotating habitats from asteroid materials or other resources. Such habitats would not need to wait for perfect planets. They could create controlled environments. They could be repaired, expanded, or moved. They could hold communities, farms, forests, laboratories, and archives. This is not only a technological dream, it is also an astrobiological idea. It suggests that once intelligence appears, the number of habitats may no longer be limited to naturally habitable planets. A single star system could hold many constructed living spaces. If future civilizations arise under long-lived stars, artificial habitats might extend their reach and duration. The universe's future life may include both worlds born from dust and worlds built by minds. A cylinder turning softly in space could hold rain, soil, and a sky of its own. Living systems may become portable. On Earth, ecosystems are tied to places. A forest belongs to its soil, climate, water, fungi, animals, and seasons. A coral reef belongs to its temperature, light, currents, and chemistry. Life is deeply local, but technology can make parts of life portable. Seeds can be stored, microbes can be carried, genetic information can be preserved, closed ecological systems can be studied, spacecraft can transport samples. In the future, entire ecosystems may be recreated in controlled habitats, if knowledge grows enough. This idea is still young. Earth's ecosystems are complex, and recreating them is difficult. A living system is more than a collection of species. It is a web of relationships, cycles, feedbacks, and histories. Still, learning to preserve life in small, closed environments may be part of becoming a long-lived civilization. If humanity is early, then it may be early in this lesson too. Preserving life beyond Earth would require humility. It would require understanding ecosystems deeply, not treating them as simple machines. Future civilizations may carry their biospheres with them, not as trophies, but as fragile continuations of home. A seed in space is not just a seed. It is a promise that a living world can be remembered elsewhere. The future of intelligence may be quieter than expansion stories suggest. Many stories imagine civilizations spreading rapidly across the galaxy. They build colonies, fill star systems, and become visible everywhere. But a real long-lived civilization may choose slower and quieter paths. It may preserve ecosystems. It may build modest habitats. It may send small probes instead of large fleets. It may focus on knowledge, art, stability, or inward development. It may avoid disturbing worlds that may have their own chemistry or life. If humanity is early, it may be tempting to imagine a future where intelligence fills the stars, but the future could be subtler. Civilizations might expand only gently. They might remain mostly within their home systems. They might leave little trace beyond faint heat and carefully aimed signals. This would also help explain why early civilizations, if any exist, are hard to see. Advanced does not always mean loud. Mature technology may be efficient. Mature ethics may be restrained. Mature societies may not measure success by distance alone. The future universe may contain intelligence, but not necessarily a galaxy bright with obvious engineering. Some of the most enduring minds may be those that learn to leave the dark mostly undisturbed. A civilization can be early and still not alone forever. If humanity is early, then loneliness may be temporary on cosmic scales. Other civilizations may arise later. Some may appear around long-lived red dwarfs. Some may emerge on worlds that are still young. Some may grow from biospheres that are now only microbial. Some may come long after Earth's present era. Humanity may never meet them. The distances and times may be too large, yet their possibility changes the meaning of the universe. A future civilization does not comfort the present in an ordinary way, but it suggests that intelligence may not be a single event. It may be part of a longer unfolding. The universe may have room for many awakenings. They may not overlap. They may not speak. They may not share signals, but each would be a way for matter to know itself, under different stars, in different ages. This is a calm answer to cosmic silence. The sky may be quiet now, but quiet does not have to mean final. It may mean early. It may mean waiting. It may mean that life's future remains wider than life's past. A lonely beginning can still belong to a universe that will one day be less alone. The stars may be silent because many voices are still unborn. Part 7 of 9. The universe may contain many quiet beginnings. A beginning does not always announce itself. A seed beneath soil is quiet. A cloud before rain is quiet. A young ocean before life is quiet. In the same way, the universe may contain many places where life has not yet appeared, or has appeared so gently that nothing beyond the planet can notice it. A planet may have warm pools, minerals, tides, lightning, volcanic gases, and organic chemistry, yet no cells. Another may have cells, but only simple ones. Another may have microbes beneath rock, living slowly with very little energy. Another may have oceans rich with chemistry, but no complex animals. From far away, all of these worlds may look silent. This means silence can hide many different states. A planet without life and a planet with hidden microbes may both appear quiet to a telescope. A world before biology and a world early in biology may both send no message. The difference is enormous locally, but subtle across interstellar space. If humanity is early, then many worlds may be in these quiet beginning stages. They may not be empty in the long-term sense. They may be unfinished. Their stories may still be forming beneath clouds, ice, stone, or shallow seas. The stars may be silent because many worlds have not yet learned how to speak. Before a signal, there may be chemistry. Before chemistry becomes life, there may be long patience. Abiogenesis may be a rare threshold. Abiogenesis is the origin of life from non-living chemistry. It is one of the deepest questions in science. Earth shows that it happened at least once, but it does not yet show how often it happens elsewhere. The early Earth had water, minerals, energy, organic molecules, and changing environments. Somewhere in that complexity, chemistry crossed a boundary. Molecules began to store information, copy patterns, use energy, and become part of systems that could evolve. Over time, these systems became life. But the difficulty of this transition is still unknown. It may be common when the right ingredients exist. It may be rare even on habitable planets. It may require special environments, special sequences, or long periods of trial and error. If abiogenesis is rare, then many planets may wait for billions of years without life beginning. They may have oceans and air, but no cells. They may be habitable in principle, yet biologically quiet. If abiogenesis is common, then life may appear often, but perhaps mostly as microbes. Either way, the universe can remain silent. A planet with early microbes does not build radio telescopes. A planet without life does not either. The first step from chemistry to life may be one of the quietest steps in the cosmos. It may happen in a pool, a vent, a mineral surface, or an unseen ocean, without a sound reaching the stars. Life may begin many times and remain simple. On Earth, simple life dominated for most of the planet's history. Microbes appeared early, and for billions of years they were the main form of life. They transformed the planet slowly. They changed chemistry, cycled elements, and eventually helped oxygen accumulate in the atmosphere. Complex life came much later. Large animals, forests, flowers, birds, mammals, and humans are recent compared with the age of life itself. This suggests that even if life begins easily, complexity may not follow quickly. A world can be alive and still remain simple for an immense time. It can have microbial mats, subsurface colonies, ocean chemistry, and biological cycles without visible animals. It can change its atmosphere slowly without producing intelligence. It can be rich in life locally, yet invisible as a civilization. If many planets follow this pattern, the galaxy may contain life that does not announce itself. Its silence would not be the silence of dead worlds. It would be the silence of small living things, patient and hidden. This is a gentle possibility. The universe may be more alive than it looks, but less technological than imagination expects. A microbial planet may be a living world with no voice. Its story is written not in signals, but in molecules, sediments, and time. Complex cells may be one of life's great delays. Complex life on Earth depends on eukaryotic cells. These cells have internal structures, including a nucleus and mitochondria. They are much more complicated than bacteria and archaea. They made larger bodies, complex tissues, animals, plants, fungi, and eventually humans possible. The origin of eukaryotic cells may have been a rare and important step. One major idea is that mitochondria began as bacteria that entered into partnership with another cell. This symbiosis gave complex cells a powerful energy system. With more energy available, cells could support larger genomes, internal organization, and new forms of life. If such a partnership is rare, then many living planets may remain microbial forever. Life may begin, adapt, and persist, but never cross into the kind of complexity that leads to animals or technology. A planet could be alive for billions of years and still never develop creatures that look at the sky. This makes humanity's early arrival more subtle. Earth may not be early in life, but early in complex awareness. The universe may contain many living worlds where the step to complexity has not happened yet, or may never happen. The path from a microbe to a mind is not a straight road. It is a long branching forest, and many paths may never reach the stars. Oxygen changed Earth slowly. Earth's atmosphere did not always contain abundant oxygen. For a long time, early life existed in a world with very little free oxygen. Then photosynthetic microbes began producing oxygen as a byproduct. At first, oxygen reacted with rocks, minerals, and dissolved iron. Only later did it begin to build up in the air. This transformation took immense time. The Great Oxidation Event changed Earth's atmosphere more than 2 billion years ago. But oxygen levels continued to vary afterward. The rise of oxygen helped make energetic complex life possible, but it did not happen overnight. On another planet, oxygen may rise slowly, weakly, or not at all. Photosynthesis may never evolve. Oxygen may be consumed by geology as fast as biology produces it. A planet may remain alive, but never become oxygen-rich. This matters because oxygen is both a biosignature and a biological opportunity. It can help distant astronomers notice life, and it can help complex organisms use energy efficiently. Without it, a world may remain biologically limited. If humanity is early, perhaps many living planets are still before their oxygen chapters. Their skies may be quiet, their life hidden, their future still waiting. A world may breathe for billions of years before its breath becomes visible from space. Animals may require a rare balance. Animals are not just larger microbes. They need energy, oxygen, or another efficient metabolism, stable development, ecological relationships, and environments where movement is useful. They need bodies that can grow, sense, respond, and reproduce in complex ways. On Earth, animals appeared after billions of years of microbial life. Their rise depended on many planetary conditions: oxygen levels, ocean chemistry, climate stability, nutrients, genetics, and ecological interactions all mattered. The exact path is still studied. On another living world, animal-like complexity may be delayed or absent. Life may remain as mats, films, colonies, or simple multicellular forms. It may not produce nervous systems. It may not produce fast movement. It may not produce anything that resembles technology. This suggests that the universe can be biologically rich while still quiet. Even planets with complex ecosystems may not produce intelligence. A reef can be beautiful without building a telescope. A forest can be alive without sending radio waves. Humanity's existence depends on a long chain of biological transitions. Each transition took time. Each one may have been uncertain. A planet does not become technological just because it becomes alive. Between a cell and a civilization, there are many silent wonders. Intelligence may not be evolution's destination. It is easy for humans to imagine intelligence as the goal of evolution, because intelligence is how humans understand their own success. But evolution has no final destination. It favors traits that help organisms survive and reproduce in particular environments. Bacteria are successful. Trees are successful. Fungi are successful. Ants, fish, grasses, whales, and microbes all represent different ways of living. None is a failed attempt to become human. They are complete in their own ecological contexts. On another planet, life may adapt beautifully without producing technology. It may become efficient, resilient, cooperative, or long-lived. It may fill oceans, soils, skies, and rocks, but it may never develop abstract reasoning, mathematics, or engineering. Even on Earth, many intelligent animals do not build civilizations. Dolphins, elephants, crows, octopuses, and apes show forms of intelligence, but only humans built radio telescopes. Intelligence exists in many shades, and technology is only one narrow branch. If humanity is early, future intelligence may appear elsewhere only rarely, after many planets have already spent long ages as living but non-technological worlds. The universe may not be trying to make civilizations. It may simply be making life, in whatever forms can endure. Tool use depends on bodies as well as minds. A mind may be curious, but technology also needs a body that can manipulate the world. Human hands are important. Opposable thumbs, precise grip, upright posture, vision, speech, and social learning all help technology accumulate. An intelligent creature without suitable manipulators might understand much but build little. A dolphin-like species may be intelligent, social, and communicative, but underwater tool-making faces limits. An octopus-like species may be clever and dexterous, but short lifespans and different social patterns may affect cumulative culture. A bird-like species may use tools, but large-scale construction may follow another path. Technology depends on a partnership between brain, body, environment, and culture. The same intelligence in a different body might never produce machines. A planet could hold minds that dream, remember, communicate, and solve problems, yet never make fire, metal, or telescopes. This helps explain why the universe may be quiet, even if intelligence is not impossible. The road from thought to signal requires many physical conditions. A creature must not only wonder, it must be able to change matter in durable ways. A civilization begins when curiosity can touch the world and leave a mark. The shape of a hand can influence the shape of a future. Language may be common, but science may be rare. Many intelligent beings on Earth communicate. Birds sing, whales call, primates gesture, bees dance. Humans speak, write, and store knowledge symbolically. Language allows thoughts to move between minds and across generations. An alien species might develop rich communication without developing formal science. It may have songs, stories, maps, social memory, and practical knowledge. It may understand seasons, animals, chemistry, or navigation in its own way. But science requires more than knowledge. It requires systematic testing, measurement, correction, and shared methods. Science also benefits from instruments. Instruments extend the senses. A telescope turns the sky into data. A microscope reveals hidden life. A spectroscope reads light. Without suitable materials, stable institutions, and cumulative records, scientific knowledge may grow slowly. This means a planet could have language for a long time before it develops astronomy. It could have culture without physics. It could have wisdom without machines. Its inhabitants may ask deep questions, but not send signals into space. If humanity is early, then future civilizations may spend long eras in rich pre-scientific states. From Earth, they would be silent. The universe may contain stories that never become transmissions. A song beneath an alien sky may be meaningful, even if no radio wave carries it outward. Technology may appear briefly. Earth's technological phase is very recent. Radio communication, spaceflight, computers, and modern astronomy occupy only a tiny fraction of the planet's history. If technological civilizations commonly last only short periods, their overlap in time may be rare. This does not require dramatic endings. A civilization may stop using loud radio. It may become more efficient. It may switch to communication methods that leak less energy. It may choose quietness. It may stabilize locally. It may transform into forms not easy to detect. From far away, a civilization may be visible only during a short window. Before the window, it is pre-technological. After the window, it may be too quiet, too efficient, or too different to notice. Searching for such civilizations becomes like listening for brief notes across an enormous night. If humanity is early, this short window problem becomes stronger. Not only may few civilizations exist now, but those that do may not be easy to catch at the right moment. The galaxy could contain many brief sparks, separated by dark intervals. A spark is real, even if it fades before another spark appears nearby. Advanced technology may become harder to detect. A young technological civilization may be noisy. It may leak radio signals, light cities, launch chemical rockets, and change its atmosphere. A more advanced civilization may become more efficient. It may waste less energy. It may use tight beams instead of broadcasts. It may build systems that blend into natural backgrounds. Human technology already shows this pattern in small ways. Many communications are becoming more directed, digital, or fiber-based. Not all signals leak into space strongly. A distant observer might find modern Earth only under favorable conditions. An older civilization could be even quieter. It may understand the cost of energy. It may value privacy. It may protect its environment. It may avoid altering its star system in obvious ways. It may build small, stable habitats rather than giant structures. This possibility changes expectations. Advanced does not necessarily mean visible. A civilization can be powerful and still leave only subtle traces. It can become less like a bonfire and more like a carefully shielded lamp. If the universe contains mature civilizations, their silence may not be emptiness. It may be refinement, restraint, or simply efficiency. The first detectable civilizations may be unusual. The civilizations easiest to detect may not be the most common. A loud civilization may be easier to find than a quiet one. A wasteful civilization may produce more heat than an efficient one. A rapidly expanding civilization may leave more signs than a stable one. A civilization that broadcasts intentionally may be easier to hear than one that does not. This creates a selection effect. The first civilization humanity detects, if one is ever detected, may not represent ordinary cosmic intelligence. It may be unusually loud, unusually nearby, unusually timed, or unusually willing to announce itself. The same is true for biospheres. The first alien life found may not represent all life. It may be life in a place easy to sample, such as Mars or an icy moon plume. Or it may be a planet with a strong atmospheric signal. Hidden life may be more common, but harder to notice. This means the search must remain humble. Discovery will be shaped by what instruments can see. Absence of evidence in one category does not erase quieter categories. If humanity is early, the first answers may be partial. They may point toward a larger hidden story. The easiest voices to hear are not always the most typical voices. They are simply the ones that reach the listener first. Humanity's own signal is fragile. Earth has been leaking some radio waves for about a century, but these signals weaken with distance. They spread out, mix with noise, and become hard to distinguish from natural background. Strong radar signals are more detectable in narrow directions, but they are not sent everywhere all the time. From far away, Earth may not be obvious as a technological planet. Its strongest sign may be atmospheric chemistry, oxygen, water vapor, methane in context, and other possible biosignatures. Its city lights would be extremely difficult to see across interstellar distances with current human technology. This is humbling. Humanity often asks why it has not detected others, but Earth itself would be difficult for others to detect unless they were nearby, patient, and well-equipped. The galaxy may contain many worlds just as subtle. If human civilization becomes quieter over time, its detectable phase may be brief. Future Earth might preserve knowledge while sending fewer accidental signals into space. It might become more advanced and less visible. A planet can be full of thought and still look like a pale dot. From the stars, even a noisy world may whisper. The galaxy may be out of sync. Two civilizations can exist in the same galaxy and never overlap. One may arise, flourish, and fade long before another begins. Their worlds may be separated, not only by space, but by time. Signals sent by one may pass through a region before the other has built receivers. Later, the receivers may listen after the signal has already gone. This timing problem is immense. The Milky Way is about 100,000 light-years across. A message from one side to the other takes tens of thousands of years. A civilization must remain detectable for long periods if others are to notice it. If humanity is early, then the timing problem becomes even deeper. Many future civilizations may not exist yet. Some past civilizations, if they ever existed, may be gone or quiet. The present could be a thin slice through a much larger story. The galaxy may not be empty. It may be unsynchronized. Its possible minds may flicker at different times, under different stars, with little overlap. A choir cannot be heard as a choir if every singer appears in a different century. Cosmic silence may be the sound of time not lining up. Messages may travel after senders are gone. A radio signal, once sent, keeps moving outward at the speed of light. It can cross interstellar distances, long after the civilization that sent it has changed or disappeared. In this way, communication across space is also communication across time. If humanity ever receives a signal from another civilization, it may not be a live conversation. It may be an old message. The senders may have evolved, moved, become quiet, or vanished. The signal would still matter. It would prove that minds existed elsewhere, at least when the message began. The same is true for Earth signals. Some of humanity's radio waves are already traveling through nearby space. They are faint, but they are part of Earth's outward history. They carry pieces of a particular era, moving into distances humans may never visit. This makes the search for intelligence feel like archaeology, with light. Astronomers are not only looking across space, they are looking into other times. Every star is seen as it was when its light began the journey. A message from the stars may be a fossil of awareness. It may not say we are here, but we were here, and we wondered too. Future civilizations may find our artifacts before our signals. Signals fade. Artifacts can last longer in some environments. A spacecraft drifting through interstellar space may remain intact for immense periods, though small and difficult to find. Objects on the moon can persist for long times because there is no weather like Earth's. Buried structures, if preserved, may outlast surface traces. Humanity has already sent a few spacecraft on paths that leave the solar system. Pioneer, Voyager, and New Horizons are small, quiet messengers. They will not reach another star for a very long time, and the chance that anyone finds them is tiny. Still, they are physical traces of a young technological species. A future civilization might detect old artifacts in its own system, if another species once visited or left probes. Searches for such objects are speculative, but they belong to the wider idea of technosignatures. Intelligence might leave machines, structures, or altered materials rather than active radio signals. If humanity is early, then there may be few such artifacts now. But over cosmic time, artifacts could become another layer of the universe's memory. A silent object can still be a message. Sometimes a civilization speaks by leaving something that continues to exist. The moon is a quiet archive. The moon preserves traces better than Earth in some ways. Earth has weather, oceans, plate tectonics, erosion, and life, all of which recycle and alter the surface. The moon is much quieter. Footprints, landers, and impact scars can remain for long times, altered slowly by micrometeorites and radiation. For humanity, the moon is already an archive of early spaceflight. It holds machines, tracks, experiments, and marks from human exploration. It also preserves ancient records of impacts and solar wind. Its surface is a library written in dust and stone. In a broader sense, moons and airless bodies throughout the galaxy may preserve histories. They may hold traces of impacts, chemistry, or visiting spacecraft. If civilizations ever travel, some of their most durable marks may remain on quiet surfaces without weather. This does not mean such traces are easy to find. Space is large, and artifacts are small. But the idea adds another way to think about cosmic time. Worlds can remember, even when atmospheres erase other places. The moon glows softly in Earth's sky, but it is also a silent keeper of footsteps. A quiet surface can hold a moment long after the voices are gone. Earth itself may not preserve humanity forever. Earth is alive and active. That makes it beautiful, but it also makes it poor at preserving delicate traces over deep time. Mountains rise and erode. Oceans move. Continents shift. Sediments bury and transform. Life grows over old surfaces. Volcanoes renew rock. If a future civilization studied Earth hundreds of millions of years from now, many human traces might be difficult to find. Some chemical and geological signals could remain. Plastics, isotopes, altered sediments, and fossils of domesticated species might leave clues. But cities themselves would not last like mountains. This shows how temporary technological visibility can be. A civilization can transform its world and still become difficult to detect later. Across billions of years, even strong traces can fade into geology. The same may be true of other worlds. A civilization may have existed, but if it did not leave durable space artifacts or long-lived signals, it may be hard to find. The galaxy may have memories that are faint, buried, or erased. If humanity is early, the lack of obvious ancient traces may still matter, but it may not be the whole story. Time is gentle in human moments, but powerful over planets. Even stone eventually becomes another page in a changing world. A careful civilization may leave deliberate records. Knowing that time erases many things, a civilization might choose to create records meant to last. It might place archives on airless moons, in stable orbits, inside protected vaults, or beyond its home planet. It might use durable materials, simple symbols, and redundant copies. Humanity has already made small gestures in this direction. Plaques, records, time capsules, and inscriptions attempt to speak across time. Most are symbolic, but they reveal a desire to be remembered, or at least understood. A future long-lived civilization might take this much further. It could preserve biological knowledge, language, art, science, and history in many places. It could make memory part of survival. It could recognize that a universe of long times requires messages that outlast ordinary errors. If humanity is early, preserving records may be one of the gentlest ways to participate in the cosmic future. It does not require loud expansion. It only requires care, patience, and respect for future minds. A record is a hand extended across darkness. It says softly that someone was here and tried to understand. The search for alien life may become a search for context. A single signal would be exciting, but context gives meaning. If a planet's atmosphere contains oxygen, scientists ask whether biology is the best explanation. If methane appears, they ask about geology, light, chemistry, and time. If a strange heat pattern is observed, they ask whether it could be natural. The search for life is therefore a search for patterns. One clue is rarely enough. Scientists need multiple lines of evidence: atmosphere, orbit, star, planet size, temperature, chemistry, and history. The same is true for technology. A signal, artifact, or unusual structure must be checked against natural explanations. This careful approach may feel slow, but it protects wonder from error. False certainty would make the universe seem smaller. Patience allows evidence to grow. If humanity is early, its first discoveries may be ambiguous. A possible biosignature, a strange atmospheric imbalance, a faint repeating signal, a mineral pattern, a plume from an icy moon. The answer may arrive gradually. The universe may not speak in a single sentence. It may offer hints and ask life to become patient enough to read them. The first discovery may not end loneliness. If scientists find microbes on Mars or chemical signs of life on an exoplanet, humanity will know it is not biologically alone, but it may still be technologically alone. If a biosignature is found, it may belong to simple life, not a civilization. If an ocean moon has microbes, they may never know the stars. This would be a profound discovery, but not the same as contact. It would answer one question while opening many more. Is life common? Does it often become complex? Does intelligence appear often? Does technology last? Are civilizations rare? A first discovery may make the universe feel more alive but still quiet. It may show that biology is not unique to Earth, while leaving the silence of minds unresolved. In that sense, loneliness can have layers. If humanity is early, the first confirmed alien life may be simple, hidden. It may not answer back. It may not know Earth exists, yet it would change everything. because one example would become two. A microbe beneath another sky would not speak, but its existence would whisper that life is part of the universe, not only part of Earth. A future full of life may begin with one small sign. Science often changes through small signs. A faint dip in starlight reveals a planet. A spectral line reveals a molecule. A fossil imprint reveals an ancient organism. A tiny wobble reveals an unseen companion. A subtle pattern can open a new field of knowledge. The search for life may follow the same path. Not a giant announcement, but a careful clue. A molecule in an atmosphere, an organic pattern in a sample, a plume with surprising chemistry, a repeated signal from a narrow region, a planet that refuses to fit lifeless models. Such a sign would be studied cautiously. Scientists would debate it, test it, doubt it, and observe again. The first hint may not be accepted immediately. The answer may grow stronger over years. This is fitting for a calm universe. Life may not reveal itself with drama. It may appear as a small irregularity in data, a quiet trace that asks for attention. If humanity is early, the first sign may be less like a shout and more like a candle seen from far away. A small clue can carry an enormous dawn. The universe may begin to feel inhabited, one careful observation at a time. Part 8 of 9 future telescopes may test whether humanity is early. The idea that humanity may be early is not only a poetic thought, it connects to real questions that science can slowly examine. How common are planets around long-lived stars? How often do those planets keep atmospheres? How often do they have water? How often do they show signs of biology? How often do biospheres become technological? Each answer changes the picture. If red dwarf planets often lose their atmospheres, then the future may be less friendly to life than their long lifetimes suggest. If many keep air and water, then the future may be rich with possibility. If biosignatures are found often, then life may be common. If technosignatures remain absent, then intelligence may be rare, brief, quiet, or still mostly in the future. Telescopes are beginning to approach these questions. They study exoplanet atmospheres, star activity, planetary sizes, orbits, and temperatures. They look for molecules that may hint at water, clouds, gases, and chemistry. Each observation is small, but together they begin to map the conditions where life might one day appear. The question is not answered by one planet. It is answered by patterns across many worlds. A single world may be unusual. 1,000 worlds begin to reveal the habits of the universe. The first Earth-like atmosphere may be difficult to read. Finding a planet the size of Earth is not the same as finding Earth. A distant world may have the right size and orbit, but its atmosphere may tell a different story. It may be dry, it may be cloudy, it may have too much carbon dioxide, it may have no air at all. It may be more like Venus, Mars, or something unfamiliar. Even if a planet has an atmosphere, reading it is difficult. The light passing through or reflecting from that atmosphere is faint. It is mixed with the brightness of the star. It may be affected by clouds, hazes, surface reflection, and stellar activity. A molecule seen in one context may mean something different in another. This is why astrobiology is patient. Oxygen can be produced by life, but also by some non-living processes under special conditions. Methane can be biological or geological. Water vapor can suggest habitability, but not prove life. Carbon dioxide can warm a world or overwhelm it. The first promising atmosphere may not give a simple answer. It may ask for more observations. It may become a candidate, a puzzle, a place to return to again and again. The universe may not reveal life with a single word. It may offer a faint spectrum and invite careful listening. Biosignatures may come in combinations. A biosignature is a sign that life may be present. On Earth, the atmosphere contains oxygen because of life, and methane also exists in small amounts. Water vapor, carbon dioxide, ozone, and other gases help tell the story. But no single molecule is always enough. Combinations matter. A planet with gases that should not coexist for long may suggest active processes maintaining them. Life can be one such process. For example, oxygen and methane together can be interesting because they react with each other over time. If both are present, something may be replenishing them. But even combinations need context. The star's light matters. The planet's age matters. The amount of water matters. Volcanism, impacts, surface chemistry, and atmospheric escape all matter. Scientists must ask whether non-living explanations can produce the same signal. This carefulness does not reduce wonder, it deepens it. A strong biosignature would be more meaningful because it survived careful doubt. The goal is not to believe quickly, but to understand clearly. If humanity is early, the first biosignatures may come from young or simple worlds. They may show that life has begun elsewhere, even if intelligence has not. A distant atmosphere can be a quiet page. Its gases may be the handwriting of a living planet. Technosignatures may be even harder to find. A technosignature is a possible sign of technology beyond Earth. It could be a radio signal, a laser pulse, unusual waste heat, artificial atmospheric chemicals, night-side lights, large structures, or patterns that nature would be unlikely to create. Technosignatures are difficult because technology can take many forms. Human technology is only one example. Another civilization may not use radio in the same way. It may not build bright cities. It may not release industrial chemicals. It may use energy efficiently. It may be quiet by choice or by design. This makes the search both exciting and subtle. Scientists can look for things that seem physically detectable, but they must avoid assuming aliens will behave exactly like humans. A civilization could be present and still leave no obvious sign to current instruments. If humanity is early, technosignatures may be rare, simply because few civilizations exist yet. Or they may exist, but be too faint, too brief, too different, or too far away. The absence of confirmed technosignatures today is important, but not final. A radio telescope listens to one kind of possible voice. The universe may contain voices that do not yet use that language. Future observatories may search for reflected light from distant Earths. One of the great dreams in astronomy is to directly image small rocky planets around other stars. This means separating the faint light of a planet from the overwhelming glare of its star. It is like trying to see a firefly beside a lighthouse from far away. Future telescopes may use special instruments to block starlight or cancel it out. They may study the reflected light of Earth-sized planets. In that light, scientists may search for oceans, clouds, continents, seasons, vegetation-like features, or atmospheric gases. Such observations would not only ask whether a planet is habitable, they would ask what kind of world it is. Does it have water? Does it have weather? Does it rotate? Does its surface change? Does its atmosphere look stable? Does it carry chemical hints of life? If many such worlds are found, humanity may learn whether Earth is rare, common, early, or part of a larger pattern. If most nearby rocky planets are barren, Earth's specialness grows. If many show signs of life, cosmic loneliness changes. The first true image of another pale blue dot may be small, but it could widen the known living universe. Red dwarf planets may become a major test. Because red dwarfs are common and long-lived, they are central to the question of future life. If their planets are often habitable, then the future universe may be full of long opportunities. If most are stripped, dry or unstable, then the long red dwarf era may be less life-friendly. Astronomers can test this by studying nearby red dwarf systems. They can look for atmospheres around rocky planets. They can measure stellar flares. They can model tidal locking, climate, and atmospheric circulation. They can ask whether planets close to these stars can keep water through difficult early stages. Some red dwarf systems already invite attention because their planets are small, nearby, or located near temperatures where liquid water might be possible. But possibility is only the beginning. A habitable zone is not a guarantee. It is a place to look more carefully. If future observations show that many red dwarf planets keep atmospheres, humanity's early arrival idea becomes stronger. If not, the sun-like chapter of habitability may matter more than expected. A small red star can become a very large question. Its answer may shape the future history of life. A planet can be in the right orbit and still be uninhabitable. The habitable zone is often described as the region around a star where liquid water could exist on a planet's surface. It is a useful idea, but it is not enough by itself. A planet's atmosphere, pressure, rotation, clouds, surface, geology, and history all influence whether water can actually remain liquid. Venus is near the inner edge of the Sun's habitable region in some broad definitions, but it is not habitable at the surface today. Mars is near the outer region, but its atmosphere is thin and its surface is cold and dry. Earth lies between them, and has maintained oceans for billions of years. This shows that habitability is a story, not just a location. A planet can begin with water and lose it. It can freeze. It can overheat. It can lose air to space. It can become chemically stable but lifeless. It can have hidden life underground while its surface looks barren. When considering whether humanity is early, this matters deeply. Counting planets in habitable zones may overestimate life, but ignoring them would miss where life might begin. The truth is found by adding layers. Orbit is the first doorway. The planet's history decides whether the doorway opens. The search for life in the solar system remains important. Distant exoplanets are fascinating, but the solar system is the only place where humanity can currently send spacecraft, landers, orbiters, and sample return missions. Nearby worlds allow close study. They let science touch rock, ice, gas, dust, and chemistry directly. Mars preserves ancient landscapes shaped by water. Europa may hide a deep ocean beneath ice. Enceladus sends plumes into space, giving spacecraft a way to sample material from its interior. Titan has lakes of methane and ethane, a thick atmosphere, and complex organic chemistry. Venus may reveal how Earth-like planets diverge. These worlds may not answer whether civilizations are common, but they may answer whether life can begin more than once in one solar system. If even simple life is found nearby and shown to have an independent origin, the meaning would be enormous. It would suggest that life may appear readily when conditions allow. If no life is found, that also teaches something. It may mean life needs more specific conditions, or that signs are hard to preserve, or that the right environments are rarer than hoped. The nearest worlds are not small questions. They are the first stones in the path toward understanding life everywhere. Mars may hold memories rather than life. Mars today is cold, dry, and thin-aired at the surface, but ancient Mars had rivers, lakes, minerals formed in water, and environments that may once have been more habitable. It may have had a thicker atmosphere and warmer conditions in its early history. If Mars ever had life, it may now be gone from the surface, hidden underground, or preserved only as traces. Ancient rocks may hold chemical patterns, textures, or organic molecules that hint at past biology. Finding such evidence would be difficult. It would require careful sampling, comparison, and protection from contamination. Mars is important because it shows how a world can pass through a habitable chapter and then change. If Mars was once alive but is now quiet, it would be a powerful example of temporary habitability. It would show that life can begin and then retreat, leaving only faint records. This connects to humanity's early arrival question. Many worlds may have windows that open and close. Some may become habitable too briefly. Others may remain habitable long enough for life, but not intelligence. A dry valley on Mars may be a memory of water, and perhaps, in the deepest hope, a memory of life. Europa may represent hidden habitability. Europa, one of Jupiter's moons, is covered in ice. Beneath that ice, evidence suggests a global ocean may exist. Tidal forces from Jupiter and neighboring moons flex Europa's interior, creating heat. That heat may help maintain liquid water below the frozen surface. If Europa has a rocky seafloor in contact with water, chemical energy may be available. Hydrothermal activity could create environments somewhat analogous to deep-sea vents on Earth. Life, if it exists there, would likely be hidden, microbial, and far from sunlight. Europa matters because it separates habitability from surface comfort. Its surface is cold and irradiated, but its interior may be more interesting. A telescope observing a moon like Europa from far away might not easily know what lies beneath the ice. If many icy moons in the universe have hidden oceans, then life may be more common than visible surface habitability suggests. But such life would also be quiet. It would not build radio telescopes. It might never see stars. A hidden ocean can be a living possibility wrapped in silence. The surface may look still, while chemistry moves in the dark below. Enceladus sends whispers from its ocean. Enceladus, a small moon of Saturn, has geyser-like plumes that spray water vapor, ice grains, and other materials from its south polar region. These plumes likely come from a subsurface ocean. Spacecraft have detected salts and organic molecules in the material, making Enceladus one of the most intriguing places in the solar system. The wonder of Enceladus is that its ocean is not completely sealed away. It sends samples into space. A future mission may fly through the plumes and study them more carefully, searching for chemical signs that might suggest habitability or even biology. If life exists there, it would probably be simple. It would live in a dark ocean, powered by chemical energy rather than sunlight. It would not answer the Fermi Paradox with a signal, but it would transform the meaning of life in the universe. Enceladus shows that small worlds can be surprising. A moon only a fraction of Earth's size can hold heat, water, chemistry, and perhaps the ingredients for life. Sometimes the universe places its most interesting clues in quiet, icy places. A plume rising from a moon can become a message from an unseen sea. Titan expands the idea of chemistry. Titan, Saturn's largest moon, has a thick atmosphere rich in nitrogen, with methane clouds, hydrocarbon lakes, and complex organic chemistry. Its surface is extremely cold, so liquid water is not stable there in the way it is on Earth. Yet Titan remains fascinating because it shows how complex chemistry can happen in environments very different from Earth. Some scientists wonder whether Titan could host unusual chemistry on its surface, or more familiar water-based chemistry in a subsurface ocean. It may not be alive, but it is chemically rich. It may show how organic molecules form, gather, and change in cold planetary environments. Titan matters because the origin of life is partly a chemistry question. Before cells, there must be molecules. Before biology, there must be patterns that can store, react, and organize. Titan is like a natural laboratory for complex organics. If humanity is early, many future worlds may pass through long chemical stages before life begins. Titan-like places may represent a step along that path, where chemistry becomes rich but not yet biological. A world can be not alive and still deeply relevant to life. Chemistry may spend ages rehearsing before the first cell appears. Venus teaches caution about Earth-like worlds. Venus is nearly the same size as Earth, yet its surface is extremely hot under a dense atmosphere. From far away, without detailed knowledge, a Venus-like planet might be mistaken for a promising rocky world. Its size alone would not reveal its true condition. This is a useful warning for exoplanet studies. A planet near Earth's size and orbit may not be Earth-like. It may have runaway greenhouse conditions, thick clouds, little water, or an atmosphere shaped by a very different history. Planetary habitability depends on climate evolution, geology, chemistry, and stellar radiation. Venus also raises questions about lost habitability. Did it ever have oceans? If so, how long did they last? Could it once have been more temperate? The answers are still studied, and they matter for understanding how rocky planets change. If many Venus-like worlds exist, then Earth-like size may be common, while Earth-like habitability remains rare. If some Venus-like worlds had brief habitable windows, then life may need both opportunity and timing. Venus shines beautifully in Earth's sky, but its beauty carries a lesson. A planet can look like a jewel and still keep a difficult surface beneath its clouds. Earth may be the control case for life. Every search for life elsewhere begins with Earth. It is the only known living planet. Its atmosphere, oceans, geology, biosphere, and history provide the only confirmed example of how life changes a world. This makes Earth both precious and scientifically important. Scientists use Earth's past to understand what a living planet might look like at different ages. Early Earth had little oxygen. Later Earth had rising oxygen. Modern Earth has complex life, forests, cities, and satellites. If observed from far away at different times, Earth would not always look the same. This helps astronomers avoid narrow thinking. A planet without modern Earth-like oxygen might still be alive. A planet with life might not have forests. A planet with microbes might be hard to distinguish from a lifeless world. Earth's history teaches that life's signs evolve. If humanity is early, Earth may also be an early reference point for future science. It may teach later generations how one biosphere began, changed, and became aware. To study Earth is not to look away from the cosmos. It is to study the only known place where the cosmos became alive. The fossil record shows how long beginnings can be. Earth's fossils reveal that life did not rush toward complexity. The earliest evidence of life is ancient, but large complex organisms came much later. For most of Earth's history, life remained microscopic. Then, over time, new forms appeared, diversified, and transformed the planet's surface. The fossil record is incomplete, but it still shows the patience of evolution. It shows that long intervals can pass before major transitions. It shows that environments change, life responds, and new possibilities open gradually. This matters when imagining other worlds. A planet may be alive for billions of years before becoming visibly complex. Another may never leave microbial stages. Another may develop complexity only after a specific atmospheric or geological change. If humanity is early, then many living planets may currently be in their long quiet beginnings. They may have chemistry and cells, but no animals. Or animals but no intelligence. Or intelligence but no technology. Their futures may still be waiting. The fossil record is not only Earth's memory, it is a reminder that life often builds its greatest changes slowly. The universe may be full of almosts. There may be planets almost like Earth, but too dry, worlds almost habitable, but too active, moons almost alive but missing one ingredient, biospheres almost complex but limited by energy, intelligent species almost technological, but lacking fire, metals, or stable culture. The universe may not divide neatly into living and lifeless, advanced and simple, empty and inhabited. It may contain many intermediate states. Chemistry may approach life without crossing the threshold. Life may approach complexity without becoming technological. Intelligence may approach science without reaching the stars. These almosts are not failures. They are natural outcomes in a universe of variety. Each world follows its own history. Some histories open toward life. Some pause. Some close. Some continue in ways difficult to recognize. If humanity is early, the galaxy may contain many almosts that will become more later, or remain quietly themselves. The silence may come from these unfinished or hidden states. This idea makes the universe feel less empty and more textured. Not every quiet world is the same kind of quiet. Between stone and signal, there may be countless soft stages. The galaxy may be waiting in more ways than one. Patience may be the main scientific instrument. Space telescopes, radio arrays, probes, spectrometers, and laboratories are all instruments. They gather data and extend human senses. But another instrument is patience. Without patience, evidence is misread. With patience, faint patterns become clear. The search for life requires returning to questions again and again. A possible signal must be checked. A possible biosignature must be modeled. A promising planet must be observed more than once. A sample must be protected, tested, and compared. A strange result must be allowed to remain strange until understanding improves. This patience is not passive, it is active care. It builds instruments, preserves data, trains new scientists, and keeps curiosity steady across generations. It understands that the universe is not hiding answers for dramatic effect. It is simply large, old, and subtle. If humanity is early, patience becomes even more important. The answer may not be ready. Other civilizations may not exist yet. Biospheres may still be forming. The search may be less like opening a door and more like watching a dawn. A patient civilization can learn from silence without being defeated by it. The stars reward the kind of attention that does not hurry them. Humanity may be the universe learning to wait. Human beings are often restless. A lifetime is short. A career is shorter. A telescope proposal, a mission, or an experiment can take years or decades. The universe, by contrast, moves across billions of years. Its answers unfold slowly. To study life in the universe, humanity must stretch its sense of time. It must imagine planets before life, life before complexity, complexity before intelligence, and intelligence before signals. It must accept that some answers may belong to future generations. In this way, astronomy teaches a new kind of patience. It invites a young civilization to think beyond itself, to gather knowledge not only for now, but for later, to preserve curiosity when certainty is unavailable, to let questions remain open without losing wonder. If humanity is early, then one of its first tasks may be learning how to wait well, not waiting with emptiness, but waiting with observation, care, and humility. The silence of the universe may be teaching the first known listeners how to listen. And perhaps listening is one of the earliest forms of wisdom. The future may answer with life, not words. When people imagine contact, they often imagine messages, voices, signals, mathematics, a deliberate greeting crossing space. But the first answer may not be a message at all. It may be a biosignature, a fossil, a microbe, a chemical imbalance, a plume from an icy moon. A planet whose atmosphere looks alive. Such an answer would not speak in language. It would not know Earth. It would not end the search for intelligence. But it would show that life belongs to the universe more than once. It would change the question from can life happen elsewhere to how often does it happen and how far can it go. If humanity is early, this may be the right first answer. Not another civilization, but another beginning. Not a neighbor waving from the stars, but a sign that the universe has begun making life in more than one place. A living cell elsewhere would be quiet, yet in its silence, it would say more than any empty sky ever could. Early does not mean alone forever. The word early carries hope and uncertainty together. It does not claim that future life is guaranteed. It does not promise that civilizations will fill the galaxy. It simply opens the possibility that the universe's silence is partly a matter of timing. Humanity may live during an early age of awareness. Some living worlds may exist now, but remain hidden. Some future living worlds may not yet be born. Some civilizations may appear later, under stars that will outlive the sun by enormous spans. Some may never know Earth existed. Others may ask the same question beneath unfamiliar skies. This thought keeps curiosity alive. It makes the universe feel unfinished, not empty. It allows silence to be spacious, rather than final. It places Earth inside a larger story, not as the center, but as the first known page. Whether humanity is early, rare, or simply unknowing, the question remains beautiful. It asks science to keep looking outward, while caring for the living world that makes looking possible. The night is quiet now, but quiet is not the same as never. Part 9 of 9 Humanity may be early, but not certain. The idea that humanity is early is not a final answer. It is a possibility. It sits beside other possibilities, each one offering a different way to understand the quiet universe. Life may be rare. Life may be common but simple. Complex life may be unusual. Technology may be brief. Civilizations may be quiet. Distances may be too large. Signals may be too weak. Or many future living worlds may not yet have begun. Science does not need to choose too quickly. It can hold several ideas at once, then let evidence slowly sort them. This is one of the gentlest strengths of science. It can wonder without pretending. It can imagine without claiming. It can listen without forcing the night to answer before it is ready. Humanity being early would explain some of the silence, but it would not explain everything. There are older stars than the sun. There are planets that may have had more time. If civilizations commonly appeared quickly, some should already be visible. The fact that none have been confirmed still matters. So the question remains open, and that openness is part of its beauty. A quiet universe does not give one simple explanation. It gives a field of possibilities, all glowing softly in the dark. The Copernican principle asks for humility. For centuries, science has learned again and again that Earth is not the center of everything. Earth is not the center of the solar system. The sun is not the center of the galaxy. The Milky Way is not the only galaxy. Humanity is not physically placed at the universe's center. This pattern is sometimes connected to the Copernican principle, the idea that humans should not assume they occupy a special place. It encourages humility. It reminds science to be careful before calling Earth unique, early, central, or privileged. At first, the idea that humanity may be early can sound like a special claim. It may seem to place humanity in an unusual moment, but unusual does not mean central. A civilization can be early without being the purpose of the universe. A planet can be rare without being the center. A moment can be important without being chosen. The Copernican principle is not a rule that Earth must be ordinary in every way. Earth is already special in one confirmed sense. It is the only known living world. The question is how special, completely unique, one of many, or one of the first few examples science has noticed. Humility does not mean assuming Earth is meaningless. It means letting evidence decide how Earth belongs. The anthropic principle notices where observers can appear. There is another quiet idea called the anthropic principle. In simple form, it says that observers can only find themselves in places and times where observers are possible. Humanity should not be surprised to live on a planet that supports life, because a lifeless planet would have no one asking the question. This sounds obvious, but it matters. Earth's conditions may seem astonishingly suitable because humans evolved under those conditions. The planet has liquid water, a stable climate history, useful chemistry, and a star that lasted long enough. If those things had not been true, no human mind would be here to wonder about them. The anthropic principle can also apply to cosmic timing. Humanity observes the universe at a time when observers are possible. Not too early, before heavy elements and planets. Not too late, after Earth's habitability is gone. This does not prove humanity is early, compared with all possible future observers, but it helps frame the question. A civilization can only wake during a window that allows waking. The window may be narrow or wide. It may occur early or late in the total history of habitability. Science must compare Earth's timing with the possible timings of other worlds. The universe is not observed from outside. It is observed from a small place where observation became possible. Most possible observers may live far in the future. Some scientific arguments suggest that if planets around long-lived stars can support life, then many possible observers might arise much later than humanity. Red dwarfs are numerous. Their lifetimes are enormous. Their planets, if habitable, could provide vast amounts of time for biology to unfold. If that is true, then humanity's current era may be early, compared with the majority of possible life-bearing time. Most observers, in a broad cosmic sense, might not exist yet. They may belong to worlds orbiting dim stars in eras far beyond the Sun's present age. This is not certain, because red dwarf habitability is uncertain. A long-lived star helps only if its planets can keep atmospheres, water, and stable conditions. Many may not. The early activity of red dwarfs may reduce their suitability. Some planets may be stripped or dried, others may survive. Still, the idea is powerful. It shifts attention from the number of planets today to the total number of habitable years across the future. If the future contains many more living opportunities than the past, then humanity may be among the earlier observers. The night sky may feel ancient, yet compared with the possible future of small stars, it may still be young. Earth's life appeared early in Earth's history. There is one fact that complicates the mystery in a beautiful way. Life on Earth seems to have appeared relatively early after the planet became suitable. The exact timing remains studied, but the evidence suggests that life has been here for most of Earth's history. This could mean that life begins easily when conditions are right. If so, simple life may be common across the universe. Many planets with water, chemistry, and energy might become alive. The galaxy could contain microbial worlds, hidden biospheres, and living oceans. But early life on Earth does not guarantee that complex life appears easily. Earth's microbes lived for billions of years before complex organisms transformed the surface. The step from simple life to complex life may be harder. The step from complex life to intelligence may be harder still. The step from intelligence to technology may require even more specific conditions. So Earth offers two lessons at once. Life may begin quickly, but complexity may take a very long time. This fits the idea of a universe that may be alive in many places, yet still quiet. The first cell may not be the rarest part. The rarest part may be the long chain from cell to civilization. The delay before complex life may be important. For much of Earth's story, the planet was alive but not visibly complex. Microbes shaped the air, the oceans, and the rocks. They built chemical cycles and changed the planet slowly, but they did not build forests, animals, or instruments. Complex cells arrived long after life began. Large multicellular organisms appeared later still. Animals diversified only in the final portion of Earth's history. Human technology appeared at the very end, like a small lantern lit after an enormous dusk. If this pattern is common, many living planets may remain simple for most of their habitable lives. Some may never cross the thresholds that led to complex life on Earth. Others may cross them, but much later. Around longer-lived stars, these delays could stretch across even greater times. This helps explain why humanity might be early in the age of technological awareness. Even if life begins often, the steps toward detectable intelligence may usually take longer than the current universe has allowed for many worlds. A planet may be alive for ages before it becomes visible as alive. It may be aware for only a moment before its starlit window changes. The silence may be made of many quiet filters. The Great Filter is often imagined as a single difficult step that stops life or civilization from becoming common. But the universe may not have one filter. It may have many gentle filters, each one reducing the number of worlds that become detectable. Some planets never become habitable. Some become habitable but never alive. Some become alive but remain simple. Some become complex but not intelligent. Some become intelligent but not technological. Some become technological but not loud. Some become loud but only briefly. Some send signals that never reach a listener at the right time. None of these filters has to be absolute. Each can be partial. Together, they create silence. The silence may not come from one wall, but from many narrow passages. This layered view is calm and careful. It does not require the universe to be empty. It does not require civilizations to be common. It allows many kinds of worlds to exist, many kinds of life to remain hidden, and many possible futures to remain unopened. If humanity is early, timing is one filter among many. It works together with chemistry, biology, geology, technology, and distance. The universe may not be silent for one reason. It may be silent because many quiet reasons overlap. A young civilization can only search with young tools. Humanity has only recently begun looking for life beyond Earth in a modern scientific way. Radio astronomy is young. Exoplanet science is very young. The first confirmed planets around sun-like stars were found only in the last few decades. The study of exoplanet atmospheres is even younger. This matters. The search has barely begun compared with the age of the galaxy. Humanity has examined only a tiny fraction of possible stars, frequencies, signals, planets, and atmospheric conditions. It has listened with limited tools for a short time. A quiet result from a young search is not the same as a final silence. It is a beginning. The first maps of an ocean do not reveal every island. The first telescope does not reveal every galaxy. The first radio survey does not hear every possible civilization. This does not mean discoveries are guaranteed. It means uncertainty remains large. Better telescopes, longer searches, and wiser methods may change what is known. Future generations may look back on the present as the dawn of astrobiology. Humanity is not only early in the universe, perhaps. It is certainly early in the search. The exoplanet revolution changed the question. For a long time, humans did not know whether planets were common around other stars. They could imagine them, but not count them. Now observations show that planets are widespread. The galaxy is filled with worlds, gas giants, rocky planets, super-Earths, mini-Neptunes, hot planets, cold planets, and systems very different from our own. This changed the question of life. It is no longer whether planets exist elsewhere. They do. The question is what kinds of planets can become habitable, how long they remain habitable, and whether life appears on them. This discovery makes the silence more interesting, not less. A galaxy filled with planets gives life many possible stages, yet no confirmed alien life has been found. This could mean life is rare. It could mean life is hidden. It could mean technology is rare. Or it could mean the search is still far too young. Exoplanets also show that the universe is more creative than old imagination expected. Many systems do not resemble the solar system. Planets can orbit close to their stars, circle two stars, lock into resonances, or exist in sizes between Earth and Neptune that our solar system lacks. The universe has many worlds. Now science is learning which of them can become homes. The next step is reading alien air. A planet's atmosphere is one of the best clues to its nature. Air can carry signs of temperature, chemistry, water, clouds, pressure, escape, geology, and possibly life. By studying light that passes through or reflects from an atmosphere, astronomers can search for molecules. This is delicate work. A distant rocky planet is faint. Its star is bright. Clouds can hide lower layers. Stellar activity can complicate measurements. The same molecule can mean different things in different contexts, but every improvement brings the question closer. Reading alien air may one day reveal a planet with water vapor, carbon dioxide, oxygen, methane, or other molecules in a pattern that suggests biology. Or it may reveal that many promising planets are dry, airless, cloudy, or more like Venus than Earth. Either result matters. If many planets show lifeless atmospheres, Earth may seem more unusual. If many show possible biosignatures, life may seem more common. If biosignatures appear mostly around certain stars, humanity may learn where life prefers to begin. The future of astrobiology may be written in faint spectra. A thin line of light may tell whether a distant world has learned to breathe. The first answer may arrive slowly. People often imagine discovery as a single moment. A signal is received, a microbe is found, a planet's atmosphere is confirmed as living. One day everything is unknown, and the next day everything is changed. But real discovery may be slower. A telescope may find an unusual atmosphere. Then another telescope studies it. Models are built. Natural explanations are tested. The planet is observed again. Scientists debate. Data improves. Confidence grows gradually. The first strong hint of life may remain uncertain for years. It may become more convincing one observation at a time. The world may not wake to a sudden announcement, but to a growing awareness that one distant planet is difficult to explain without biology. This slow arrival fits the quiet theme of the universe. Life may not announce itself loudly. It may appear as a pattern that careful minds learn to recognize. If humanity is early, the first answer may be even more subtle. It may not be a civilization. It may be chemistry. It may be a gas. It may be a small plume from an icy moon. It may be something that whispers, not something that speaks. The universe may answer softly, because soft answers are all that early listeners can receive. A lonely universe may still be connected by matter. Even if civilizations are rare or separated by time, everything is still connected by shared cosmic history. The atoms in Earth formed in stars. The hydrogen in water began in the early universe. The calcium in bones, the iron in blood, the oxygen in air, and the carbon in cells all belong to the same ancient process that built planets and galaxies. Every possible living world would share this history. Its organisms, if they exist, would also be made from cosmic material. Their chemistry might differ, their biology might differ, their stars might differ, but they would still be part of one unfolding universe. This connection does not require communication. A silent planet and Earth can be related through physics, chemistry, and time. Two civilizations may never meet, yet both are ways the universe becomes aware. Two biospheres may never exchange life, yet both are rooted in star-made elements. Cosmic loneliness is therefore not complete separation. It is solitude inside a shared origin. Earth is alone in knowledge, but not separate in substance. The same universe that made the stars made the questions, and the same matter that drifts between galaxies became, here, a listening mind. Future life may wonder about early Earth. If civilizations arise far in the future, they may study the ancient universe in their own way. They may look for old planets, old biospheres, and early technological species. They may wonder whether life appeared before them. They may search for traces of vanished worlds. Earth may be difficult for them to find. Its signals may have faded. Its surface may have changed. Its artifacts may be small. The sun may have evolved. The planet may no longer show the same signs it shows now. Yet perhaps some trace could remain. A spacecraft drifting through space. A record on the moon. Chemical marks in ancient rocks. A distant radio wave, faint and stretched. Or perhaps nothing clear enough to be known. This possibility gives the present a tender feeling. Humanity may become an ancient unknown to future minds. It may be one of the early civilizations they imagine but never confirm. It may be a ghost in their equations, a possibility in their models. And yet, whether remembered or not, this moment is real. Earth's life is real. Its questions are real. Its attempt to understand the universe is real. To be known forever is not required for existence to matter. A candle still gives light, even if no one later finds the wax. Humanity may become a bridge. If humanity is early, it could become a bridge between the universe's past and future. It can study the ancient light of the cosmos. It can preserve the story of Earth. It can protect life, record knowledge, and perhaps carry biology beyond one planet with care. A bridge does not own either side. It simply connects. Humanity is made from the past. Ancient stars, early oceans, microbes, evolution, and memory. Humanity also points toward the future. Telescopes, archives, spacecraft, and generations not yet born. This bridge may be fragile. It depends on choices. It depends on whether curiosity is preserved, whether knowledge is cared for, whether Earth remains a living home. A civilization is not guaranteed to become long-lived. It must learn how. But even early steps matter. Every observation of an exoplanet, every mission to Mars or an icy moon, every preserved record, every careful question becomes part of the bridge. It extends the reach of Earth's living story a little farther. The universe may not need humanity to be grand. It may only need humanity to be careful with the rare awareness it has. Being early can make Earth feel more precious. The more vast the future becomes, the more precious the present may feel. Earth is not diminished by the possibility of future life. It becomes the first known place where life has already crossed from chemistry to thought. Every forest, ocean, desert, reef, cloud, insect, bird, and human breath belongs to the only confirmed living world. Exoplanets may one day join this category, but for now, Earth stands alone in evidence. Its biosphere is not an ordinary object in a list. It is the list's beginning. If humanity is early, then Earth is not just home. It is an early archive of life. It carries the story of how matter became biology, how biology became awareness, and how awareness began searching the stars. This does not make Earth separate from the cosmos. It makes Earth one of the cosmos's first known flowers, a small blue world where atoms learn to sing, measure, remember, and wonder. The search for future life should not pull love away from Earth. It should return love to Earth more deeply. The first known living world is not less special because others may one day be found. It is the reason the search can begin. The universe may be entering its age of questions. For billions of years, stars shone without being studied by minds, at least as far as science knows. Planets formed, oceans gathered, atmospheres changed, and life appeared on Earth. Then, eventually, beings looked upward and began to ask what the stars were. Perhaps this is part of a wider transition. The universe may be old in matter, but young in questions. It may be entering an age when some planets become aware of galaxies, atoms, and time. Earth may be one of the first known places where this has happened. Questions are a kind of light. They do not brighten space like stars, but they brighten understanding. A question can travel from one generation to the next. It can shape instruments. It can open fields of knowledge. It can make a small species study the whole sky. If future civilizations arise, they may also enter their own age of questions. They may ask where they are, whether others exist, how life began, and what the universe will become. The universe's age of stars began long ago. Its age of questions may still be near dawn. Early does not mean lonely in every way. Even if no other civilization is nearby, humanity is not alone in the ordinary sense. Earth is filled with life. A human being shares the planet with trees, microbes, birds, whales, insects, fungi, and countless living systems. The biosphere is a vast companionship. Cosmic loneliness is a different kind of loneliness. It is not the absence of life around us. It is the absence of confirmed life beyond Earth. It is the silence between stars. It is the unanswered question of whether other minds exist elsewhere. But the presence of Earth life matters. It means the universe has already produced connection here. Ecosystems are relationships. Breath connects organisms to atmosphere. Food webs connect species. DNA connects generations. Culture connects minds across time. Before humanity searches for distant company, it already belongs to a living world. This world is not silent. It is full of sound, color, motion, and memory. The stars may be quiet, but Earth is not. If humanity is early, Earth's living richness becomes even more meaningful. The first known answer to cosmic loneliness is the life already here. Future silence may not feel like failure. If humanity continues searching and does not find life soon, that silence will still teach. It may show that life is rare nearby. It may show that certain planets are not habitable. It may show that red dwarf worlds often lose atmospheres. It may show that biosignatures are subtle. It may refine the question. In science, not finding something can be meaningful when the search is careful. A quiet result can narrow possibilities. It can guide better instruments. It can reveal assumptions. It can make future discoveries more precise. The silence does not need to be discouraging. It can be part of learning the shape of the universe. It can teach patience, humility, and better questions. It can remind humanity that answers are earned slowly. If humanity is early, silence may be expected. The task is not to demand immediate company. It is to understand the conditions that make company possible, whether now or later. A careful listener learns from both music and pauses. The pauses may be long, but they are not empty of meaning. The question may change over time. At first, the question is simple. Are we alone? Then it becomes more detailed. Are there microbes elsewhere? Are there biospheres? Are there complex organisms? Are there intelligent beings? Are there technological civilizations? Are they present now? Are they detectable? Are they willing to communicate? The early question opens into many questions. Each one may have a different answer. Humanity may not be alone biologically, but alone technologically. Or it may share the galaxy with quiet biospheres. Or it may be one early civilization among future many. Or it may be rarer than expected. This is why the search is so rich. It is not a single door. It is a corridor of doors. Behind one may be Mars's ancient chemistry. Behind another, Europa's ocean. Behind another, exoplanet atmospheres. Behind another, the long future of red dwarf stars. The question changes because understanding grows. A child asks where the stars are. A scientist asks what they are made of. A civilization asks whether any of them are homes. The universe does not only answer questions, it teaches better ways to ask. Humanity's early moment can still be peaceful. There is a quiet emotional shape to this idea. Humanity may be early. The universe may still be young in biological time. Many future worlds may not yet be alive. Many future minds may not yet exist. The present sky may be quiet because the long story of life has barely begun. This can feel lonely, but it can also feel peaceful. A quiet beginning is not the same as an empty ending. The universe may not be withholding company. It may simply be unfolding slowly. Earth's role, then, is not to rush the answer. It is to listen, learn, care, and continue. To build instruments without losing humility. To search for life without neglecting life here. To imagine future civilizations without inventing certainty. To let wonder remain gentle. The night sky does not need to be crowded to be meaningful. A single living world beneath it is already extraordinary. A single mind wondering about future life is already part of the universe's awakening. Early light is still light. A quiet dawn is still dawn. The universe may be more future than past. Human memory naturally looks backward. History, fossils, ancient stars, and cosmic background light all point into the past. But the universe's full story may extend far beyond what has already happened. Many stars will shine for enormous lengths of time. Some planets may remain stable. Some chemistry may still be waiting. Some life may still be unborn. If humanity is early, then the universe is not mainly a finished museum. It is also a future landscape. Its greatest number of living years may lie ahead. Its most common observers may not exist yet. Its longest-lived biospheres may not have begun. This thought stretches the mind gently. The present becomes a shoreline between deep past and deeper future. Behind Earth are ancient stars, early oceans, and billions of years of evolution. Ahead may be red dwarf ages, hidden worlds, artificial habitats, future questions, and perhaps life under skies humanity will never see. The universe may be ancient and unfinished at the same time. It may have already made wonders, and still have most of its wondering left to do. The stars may be waiting without knowing they wait. Stars do not wait in a conscious way. They shine because physics guides them. Planets orbit because gravity holds them. Clouds collapse, elements form, rocks cool, oceans gather. The universe does not need intention to create possibility. And yet, from the perspective of life, it can feel as if the stars are waiting for chemistry to settle, waiting for planets to calm, waiting for cells to appear, waiting for minds to look up, waiting for questions to move from one world to another. This is poetry, not literal science, but poetry can hold the feeling of science without replacing it. The facts remain: long-lived stars, future habitability, slow evolution, uncertain life. The feeling is that the universe has time, and time allows possibility. If humanity is early, then many stars that may one day host life are simply shining through their first quiet chapters. Their planets may be young, restless, frozen, hidden, or not yet ready. Their future may be invisible from Earth. A star does not need to know it is patient. Its light is patient anyway. The final answer may be layered. At the end of this long question, the answer may not be a single phrase. It may not be simply yes, we are alone, or no, we are not. It may be layered. Life may be common in simple forms. Complex life may be less common. Technology may be rarer. Long-lasting civilizations may be rarer still. Some may arise in the future. Some may have existed in the past. Some may be hidden in oceans. Some may be quiet by nature. Some may be too far away in space or time. Humanity may be early in one sense and ordinary in another. Earth may be rare in some features and common in others. The universe may be full of planets, modest in biospheres, sparse in civilizations, and vast in future possibility. This layered answer may be more beautiful than a simple one. It allows the universe to be subtle. It allows every world to have its own history. It allows silence to have texture. The question of life beyond Earth is not only about counting civilizations. It is about understanding how matter becomes alive, how life becomes aware, and how awareness learns to care for its moment. The universe may not answer with a shout. It may answer with many soft truths, gathered slowly. The quiet sky remains open. After all the ideas, the sky is still the sky. Stars shine. Planets move. Telescopes listen. Distant light arrives from ancient galaxies. Earth turns beneath the night. The question remains open, but it is no longer empty. Maybe humanity is early. Maybe many future worlds have not yet awakened. Maybe the universe's longest biological chapters lie ahead, written under dim red stars. Maybe hidden oceans already hold quiet life. Maybe Earth is one of the first worlds where a planet became aware enough to ask about the rest. Or maybe life is rarer than hoped. Maybe Earth's path was unusual. Maybe the silence means the steps from chemistry to civilization are very difficult. Even then, the question remains meaningful, because it reveals the preciousness of what is known. There is no need to solve everything tonight. A calm mind can hold mystery without tightening around it. The universe can remain open. The stars can keep their distance. The future can remain unwritten. The quiet sky does not close the story. It turns the page very slowly. Now the journey can grow quiet. Tonight's question has moved through deep time, from the first stars to future red dwarfs, from ancient chemistry to possible civilizations not yet born. It has wondered whether humanity is late to the cosmos, or whether humanity may be early in the long age of life. It has followed the atoms made inside stars. It has watched galaxies mature like slow gardens. It has imagined planets around dim red suns, hidden oceans beneath ice, quiet microbes under stone, future telescopes reading distant air, and civilizations that may rise long after Earth's present age has passed. And through it all, the silence remained gentle, not empty, not final, just wide. Perhaps the universe is quiet because life is rare. Perhaps it is quiet because life is hidden. Perhaps it is quiet because intelligence takes time. Perhaps it is quiet because many future voices are still unborn. Perhaps humanity is one of the early lights in a very long dawn. There is no need to choose an answer now. Let the question rest softly. Let the stars stay where they are. Let distant planets continue their slow orbits. Let red dwarfs burn with patient light. Let hidden oceans move beneath their shells of ice. Let future worlds remain future worlds. Let the universe keep its long, calm rhythm. For now, there is only this moment. A quiet room, a soft breath, a dark sky beyond the window, a small blue planet turning through space, a living world full of oceans and clouds, forests and deserts, voices and dreams, carrying one young civilization beneath the stars. If humanity is early, then there is nothing to rush. The future has time. The stars have time. The universe has more time than the mind can hold. And you do not need to hold it all tonight. Let each thought loosen. Let each question drift away like a faint signal moving through deep space. Let the body grow heavier. Let the breathing become slower. Let the silence become gentle around you. You have traveled far enough for one night. From the first atoms to future suns. From Earth's living surface to the far edge of imagination. The journey has followed one peaceful possibility, that the universe is not finished becoming alive, that the quiet above us may be the quiet of an early morning, that somewhere in the deep future, under unfamiliar stars, other minds may one day look up and wonder too. And even if they never know this moment still matters. Earth has wondered, Earth has listened, Earth has looked outward with calm curiosity. And for tonight, that is enough. Let the stars fade into softness. Let the questions become dreams. Let the great future of the universe continue without needing your attention. You can rest now, here on the first known living world, under a sky that is quiet, patient, and full of possibility. And if you are still awake, and would like to keep drifting, another quiet journey is waiting for you on screen. If these calm nights bring you a little peace, you are always welcome to return and wander gently through the cosmos again, one drifting mind at a time. Sleep well and good night.